Então, vamos para aquele protocolo que a gente precisa seguir aqui. Este evento está sendo transmitido ao vivo e gravado pelo YouTube. Ao permanecer no local, o participante declara estar ciente de acordo com a captação e utilização de sua imagem e voz na transmissão e na gravação do evento. This event is being broadcast live and recorded on YouTube. By remaining in this venue, participants acknowledge and agree to the capture and use of their image and voice in the broadcast and recording of this event. Okay. So, good morning, everyone. It's a pleasure to have here Professor Dubey for this fourth and last class of his mini course on cooperative game theory. So, please, Professor Dubey, the floor is yours. Thanks.
Thank you. Up till now, we were discussing the works of Lloyd Shapley. The first lecture was on the Gale-Shapley matching. The second one was the kidney exchange, the paper of Shapley and Scarf. The third was the Shapley value and convex games, everything works of Lloyd Shapley, part of the huge volume of works by Lloyd Shapley. Today, I'll have the temerity to talk about something I'm currently working on related to the Shapley value, and I'd appreciate your feedback. There is nothing to post on this because it's still being written. And I'm giving the talk deliberately so I can get insightful criticisms and comments from you. I'll be grateful if you send them to me in writing at any time that it occurs to you. Okay, so with that, let me start. So I gave this example earlier. There are three players, one who owns the land, the other two don't own land, they need land, but they have skills. G can build a garage on that land if it was available, which would earn more money than the landlord is earning on his own. And D is a developer who could build a motel and earn even more, 20. So we can think of it as a game. G and D by themselves can achieve nothing because the landlord, they need the land which is owned by L. The landlord, if he's by himself, produces just some crops which earn 1. If the land can be used either for farming or to make a motor garage or to build a motel, just one of these three in the story that I'm telling, okay? So the landlord and L and G would be better for them to put a garage and earn 10. L and D would build the motel and earn 20. G and D together can get nothing. And L, so is the game clear? How I got it? And the question is, how should we split 20 among the three players? Okay, so we developed the notion of the Shapley value through axioms, and we could apply that universal notion to this problem and compute. Okay, but I want to now look at it another way. I say consider a different problem. Here are three, so on the left are users of facilities, and on the right are facilities themselves. Okay, so the facilities are labeled K1, K2, K3, K4, K5, and the users are 1, 2, and 3. I'm going to describe this in a different way, but first let's look at this. This is saying that player 1 has to use facilities K1, K3, and K5. So this bipartite graph shows for each player which subset of facilities he must use. There is no strategy choice here. He has to use this. This is if the facility is costly, we'll put a negative sign. If it's beneficial, it'll be positive. These are the cost of, think of them as setup. So if it's a negative, it's the setup cost of the facility. And once the facility is there, it gives out the cost or the benefit independent of the set of users who come. It's not a variable cost, okay? So this is the scenario that I have in mind. I'll show you another way to look at it. And it is to be an irrelevant question whether this is realistic, whether this has ever happened in human history. This is irrelevant, because the purpose of the Shapley value is to solve a problem that may arise. This could be happening on another planet. So long as it's a internally logically consistent situation, we want to be able to solve it. So it's a moot question whether this is realistic. Okay. Now, yes, Shmuel. -9 is a cost, 9 is a benefit. Once the facility is there, it will give to its users 9, no matter who the set of users are. The facility K1, it's not a negative cost. Once it's there, it will give a profit of 20. There may be a cost.
That's excellent, but what's the cost of setting it?
The benefit is 30, the cost is 10, so the net is 20.
And -9 means?
The cost is 9, there are no benefits.
The cost is 9, there's no benefit there.
Yeah, you can always put cost benefit and take a net,
Okay,
and that's what I'm talking about. Okay. Let me give the example another way, which may be better. So I'm going to escape, close, and I'm going to give the same example in a different way. So here, oh, sorry, I got something wrong. Control L. There are, these are airports, okay? The negative means it's the cost of building the runway at the airport. All these, the 3 planes are identical planes, and each plane has to fly according to the arrows. So all the planes are identical. How is there a +10? Well, in India, this has happened, if you want a real story, but I'm saying I don't care about reality, but in India, there have been airports in remote areas, and the government has said, here is an amount of money which I will give as to induce planes to come to our remote area, and then they have a certain amount, a budget, and they'll give it among all the users who come there. All right, these planes are identical. Now, at any airport, the user is a plane which lands and takes off. The landing and taking off is called a usage, okay? So now let's look at any airport, K3. K3 has 2 users, a red plane lands and takes off, and a green plane of the same size lands and takes off. So the K3 sees 2 users. If you put yourself in the position of the airport and just look at what's happening locally, it sees 2 planes, identical, landing and taking off, right? And so it says they are identical. Now, I ask people, how would you split costs here? We have to split the costs of all the airports. Costs I'm using, if it's negative, it's cost in the colloquial sense. If it's positive, it's a benefit in the colloquial sense. So the government has, each airport, if it's giving out money, it's a budget it has to attract flights to its location, and it's going to spend that, okay? Now, how should we, I ask people, how should we split the costs here? And I have asked people who have no mathematical knowledge, you know, fashion designers, politicians in India. And they all, And I say, this is not a trick question. So how would you split? So they would say, all right, at any airport, don't charge those who don't use it. Don't give them either cost or benefit. Only look at those who use. Second, since they are all identical, split equally. This is something which comes to your mind, even if you're not a mathematician, correct? Now I tell you, now I tell you, if you can answer that, you know the Shapley value for all games. I'm going to describe a theorem. Second, I'm going to tell you that not only do you know the Shapley value for games, but because the way games have been defined are that all coalitions are possible given a set of players, and for every coalition, we must tell you how much it can make. Right? That's the game. I want to look at games with incomplete coalitions, where many coalitions may not be feasible. And I say this approach here, which involves no coalitions, forget games. This approach opens the door to understand how to extend the Shapley value to games more general than Shapley with incomplete coalitions. That's where I'm trying to go. But I have to convince you of the validity of this way of thinking. Now, a question which you could ask, which you'd surely ask, is if Shmuel and I are in a coalition, right? And we are getting, and all users get a benefit of the 10 is split among all the users. Why don't he and I pretend to be two different users instead of acting as one at the airport K3? If there are 3 users, could we benefit by pretending to be splitting ourselves? Why should the coalition stay together? And the answer to that is that in this scenario, you have to go to a central authority as a coalition and get permission of places where you're going to land. And that central authority will not let you split it. You have to decide. You can't go to one airport and say, I'm 3 different users. Another, I'm combined as one, because you have to register in advance. And so you have to act the same way at all the airports. It is giving you the permission. And then if the game is super additive, you don't have any incentive to split. Okay, so a coalition has no incentive to pretend to be 2 disjoint coalitions. I put that as an aside. That has to be part of the story to tell the story. Okay. Now, I go back. So we wanted to solve this problem. I said, let's forget about it in order to solve it. Let's look at this problem instead. And here, so this is the same as the airport problem. It's just easier to draw it this way, okay? So a user, Mr. 1, is going to 3 airports and he's making a cycle on those 3. He goes to airport K1 first, then to K3, then to K5, and back to K1. That's what this means, okay? These are describing flights. And each plane, all the planes are identical. What is variable is the flight path. And these are costs at the airport. So this is isomorphic to the picture I drew before. Is that clear? So, okay, now, so here we are saying split I'm using the word cost. If it's negative, it's a cost in our colloquial sense. If it's positive, it's a benefit, but let me use one word. So split the cost of any facility equally among its users because the facility is user blind. Like the goddess Themis of justice, it has a blindfold. It doesn't look at who is coming. It just has something to give, no matter who comes. So it can't distinguish among the users. It's user blind if you sit at a facility. And this is the heart of the point. There is a standpoint called the K standpoint, the facility K, which tells you if you can take this local standpoint of a facility, then it provides a rationale for splitting whatever the facility is giving equally among the users, because the cost there does not depend on the set of users either at its own location or at other locations. Because it is user blind, I could now define other kinds of facilities where the cost depends on the set of users, and then this won't work. So very deliberately, we are looking at a situation where facilities are user blind, and that justifies saying, let's split equally among all the users, okay? Let's not charge people who are not using our facility. Those who are using us, I'm user blind, I don't even know how many there are, leave aside their identities. My eyes are closed. I'm giving a benefit of 10, well, or minus 10. My eyes are closed, so whoever comes, I can't distinguish between them. Therefore, I must split equally. You see, the equal split is coming from a philosophical point of view here. Otherwise, why split equally? Okay? It's because we are taking the local standpoint by sitting at a facility, not looking elsewhere, and just looking locally. All right, so this is my justification for saying split equally. All right, now, if you look at this situation, we can, if we are in the bad habit of thinking game theory, associate a game with this, okay? So for any coalition, its worth, how much it gets, is this total cost of all the facilities that its members must use. So we of 2, 3, look at 2 and 3. 2 and 3 are using K1, K2, K3, K4 and K5 together. And so we add up the total, and that's the W of 2, 3. It adds up to 0 because it's 10 plus minus 10 plus 9 plus minus 9. So you see, I can associate a characteristic function. This is if you are a game theorist. Ordinary people don't need all this. They just look there and tell you what the solution is. Well, I tell you that this game has the same characteristic function as the game before between the landlord, the 3 players, L, G, and D. And if you now assume, this is an axiom that Lloyd Shapley wrote, I later found out after writing this paper, so I'll tell you what he wrote. If you assume that the way to split costs should depend only on the financial structure that emerges from the game and no other details of the game, then the way to split here and in the previous problem must be the same. They have the same characteristic function. Okay, so this is a big assumption. Shapley wrote a paper in 1950 at the Rand Corporation. It's a working paper. Hard to get, but still available, okay? And his first axiom was, the value depends only on the characteristic function. It sounds very bizarre to us today because we take so I'm translating what he said, adding 2 words. The value of a game depends only on its characteristic function. Today we take the game to be the characteristic function. So what does it mean, his statement? Well, he had in mind that a game is the whole context. So I described 2 different games here. One is airplanes flying, and the other is landlord, developer, and a garage maker. They are 2 different games, but the costs incurred by each coalition is the same. And so Shapley's axiom is quite full of content here. It says that the way you should split costs should depend on the cost structure, never mind how you got it. Right? That's the content of that axiom. And I'm using it to the hilt when I say that we should, okay, so that's what I'm saying. Are these 2 examples clear? I have 2 different games. They have the same characteristic function. Okay? And therefore, the split, since the financial structure is the same, the division of the money should be the same. That's a big assumption, and we are making it. Okay. So this is what I wrote here. I've said it all to you in words. Now, so Given a characteristic function, we can ask, is there a way to represent it as the airport problem? And okay, there could be two things that could happen. Either we can't represent it, or then then this approach goes nowhere. Or given a characteristic function, maybe there are many representations. And if you solve each representation by this equal split user blind method, you may get different solutions. Then again, we are in trouble. So we have to ask these questions. So the idea of representation, as Professor Araujo will tell you, has a long tradition in pure math. You represent abstract things like groups identify them with some collection of linear transformations. And the group operation is composition of linear transformations, right? So the representation theory, you take something abstract and you represent it with something concrete. We are trying to do that. The characteristic function is abstract. I'm trying to represent it by flights of identical planes, okay? Or by assignment. They are the same thing. All right. And one second, I don't know which way to go. So let me start the formal theory. So now I'm going to give you some mathematical theorems based on the intuition that I have outlined. N is a finite set of players. Eta, that's funny looking thing, is the collection of all non-empty coalitions. I'm going to avoid the empty set for a while, okay? So, and C is some sub-collection of coalitions. It may not be all of them. Cert, okay? Now, I'm going to assume that N, if you take the union of all the coalitions, I get N. In other words, a player exists only through his presence in coalitions. The coalition can be a singleton also, but need not be. That's a technicality. And a game is just assigning, telling us how much money each coalition can make. So I can think of a game as a map or as a vector. These are two, you can speak in English or in Hindi. They're saying the same thing. We have a vector space with all its axes labeled by the coalitions. So how much a coalition can make is the component of the vector on that axis, which is the same as specifying a function. So sometimes I'm going to write R to the power C as the space of games. Now, I've taught you the Shapley value. When we have all the coalitions, Shapley value is computed by this formula, by the fairy tale of the random order method. People enter a room in random order. They never enter a room. There's no room. It's just a fairy tale to help you compute or remember a formula. It's justified by its axioms, right? I've said that at least 3 times now. So, but that method doesn't work here, because if all coalitions are not, it works only when all coalitions are feasible. If all coalitions are not feasible, there will always exist an order where either the predecessors of a player in the random order won't be feasible, or after he joins, it won't be feasible. So marginal contribution will not be always defined even, okay? So that formula is not going to apply even, okay? So now the idea is, as I said, to take something abstract, this map V, and to represent it concretely by an assignment. So what's an assignment? Assignment is simply two maps. One is mapping the set of players, each player, to a subset of facilities that's shown by the graph, and writing down a number, gamma, for each facility, which can be positive or negative, okay? That's what an assignment is, mathematically, correct? I gave example of it earlier. So I have now formally defined a assignment as 2 maps. The domain and the range come with the map, okay? A finite set of players a finite set of facilities for each player, a non-empty set of facilities that he must use, and for each facility, its cost, right? That's an assignment. Now, I make a definition. We say an assignment represents a characteristic function if we'll use the word game for the characteristic function. I know all of us have used this bad habit of using the word game for it instead of characteristic function, so I'll stick to that. Given a game, we'll say that an assignment represents it if, for any coalition, V of S is the sum of the costs of all the facilities that the people in S must use, and a second technical, that the set of users of a facility should also be feasible, okay? So that's an assignment. In other words, this assignment should be measurable with respect to the coalitions that are available. That's the second condition, okay? So I'll say that's what an assignment is. And given an assignment, and forgetting the game V, we have the notion of equitable distribution, which I already defined. For each facility, split its cost equally among all its users. So given an assignment, we can compute an equitable distribution without knowing game theory. In the assignment, there are no coalitions. Forget games on coalitions, right? So the assignment is sort of transparent what to do. But it represents a game in a very formal sense. All right. Now, given any assignment, we can trivially expand it. I'll come to that later. We can trivially expand it as follows. You take a facility whose cost is 10, replace it by several facilities, and assign costs arbitrarily to those copies of this facility, so that, and also assign costs arbitrarily so that the total is still the same as before. So if I have a facility with cost 10, I can create 3 facilities with cost 20, minus 15, and 5. Okay, they add up to 10. So I split it arbitrarily. And to each of these copies, I assign the same set of users. So you can always take a representation and keep expanding it trivially this way, and the equal split will remain the same. So these are called trivial expansions of an assignment. And now I state a theorem. Okay, so let me do it the way I'm doing it here. Now I want to write a condition on coalitions. So let us construct a square matrix which will have entries 0s and 1s as follows. Let's label all the rows by coalitions which are in our collection C. So C is a collection, and for convenience, I'm labeling the rows and columns by the coalitions in that C in the same order, okay? Now, here is how I define the entry of a matrix. If you are looking at an entry corresponding to row Si, labeled by coalition Si, and column by Sj, then the entry, or K, Sk, then the entry is 1 if they intersect and 0 otherwise. So this well defines a square matrix whose entries are 0s and 1s, correct? And I say that the collection C has full rank if this matrix is invertible. Okay, so now the theorem is intuitively going to be, I want the following theorem. For any game, I'm going to say it verbally, then I have written it badly here. When I rewrite the paper, I'll write it the way I'm saying it. So please just listen to me. I want a collection of coalitions which has the following property. For any game defined on them, there exists a representation. Second, for all representations, the equitable solution is the same. This is what I want, right? Because then the method of representation succeeds for this collection of coalition. Every game should have a representation, and if it has many, their equitable solution should be invariant of the representation. Okay. Theorem, this is true if and only if. It's both ways. the collection C has full rank. That's the theorem. Second theorem, when you take all coalitions, it has full rank. Third theorem, here is I want to describe collections of coalitions in the set theoretic way, which doesn't depend on the matrix and algebra. Then we say that a collection of coalitions is a quasi-algebra if whenever a set is there, its complement is there. Okay? Closed under complements. This falls short of being what is called an algebra. An algebra is closed under unions and intersections and complements. I think any two of these are enough to give the third. Yeah, that's called an algebra. And an algebra on a finite set is defined by a partition. Because the elements of the pieces in the partition are the atoms, and by taking their unions, you get the whole algebra. So you can identify an algebra with a partition. I'm asking for less. I'm asking for the collection to be just a quasi-algebra. And then if it's a quasi-algebra, it will satisfy the full rank condition. So that's, and from this we see that the collection of all coalitions has full rank. Because it is closed under complements, it's even more, it's an algebra. So therefore, it is a quasi-algebra. And so it will have full rank. Okay, so here is the thing. I defined a quasi-algebra. There is something else called hierarchy, which is a purely set theoretic definition, but I will not bore you with it. So if the big set is all collections of coalitions which have full rank. You compute the symmetric 0-1 matrix, and if it's invertible, we say, okay, it's full rank. So collections of coalitions that have full rank is a big set. Quasi-algebra, namely collections which are closed under complements, is a small subset of it. Each point in the set is a collection of coalitions. And in between, there is another set theoretic thing which I'm suppressing, not to bore you, called hierarchy. But hierarchy is important for examples I will give later. Okay, so that's the picture. And now I'm stating the same theorem that I said, but badly. I'm going to rewrite it. But I didn't have time to rewrite everything. So it says, assume C has full rank and consider any game defined on. So the idea is to extend the notion of the Shapley value to games with incomplete coalitions. That's our ambition. Okay? So I say, take any collection of coalitions on which we are going to look at all possible games. And I say that there exists a unique representation of that game with minimal number of facilities. All other representations are trivial expansions. Thus, the equitable solution is invariant across all representations. Finally, in the canonical case, which is Shapley's case, the equitable solution is the Shapley value. So that's why it's an extension. When you go to all of the Shapley value, when you go to all coalitions, you get the Shapley value. Okay? When you look at sub-collections, you get something else. But all is coming from one approach, representations of the game, of an abstract game by something concrete. Okay. And then I also have that this condition of full rank is also necessary. So here is theorem 3, forget theorem 2. If V has a representation, then V, okay. If every V has to have a representation, blah, blah, then it has to have full rank. The condition of full rank is both necessary and sufficient for the method of representations to work and to prescribe something. Okay? Otherwise, if C does not have full rank, we can construct counterexamples where there are either no representation or multiple representations with different solutions, because in the representation we solve it intuitively, split equally, right? So it's a tight condition, the full rank. Okay, I'd like now to give some properties of this solution. So when should we say, now we have a game on incomplete coalitions, when should we say that two players are symmetric? I ask you, So a player is now doing two things. First, by joining a coalition, it can make the coalition eligible, which it wasn't before. This is a problem which did not occur in the classical case when all coalitions were eligible. Therefore, when I want to see if two players are symmetric, I have to check two things. Not only the worth of the coalition that they can join, but also the eligibility. And therefore, I'm writing the definition. Are symmetric if whenever the membership or the eligibility, the membership in C or the eligibility of the coalition, if it works with I, it will also work with J. And then the worth also should be the same. Okay? So you have to put a nuance on the definition of symmetry. The first condition was tautological or automatic in the case of Shapley, because all coalitions existed. But now we have to put this additional condition in. Similarly, how would you define a dummy? The eligibility of a coalition, namely whether it is in our collection or not, should not depend on whether the player is in it or not in it. Okay, and then that coalition should also get 0. So you have to add these conditions to define dummy and symmetry. If you do it right, then our solution concept does have the property that symmetric players get the same and dummies get 0. And it also has the property of linearity. So it has all these properties. Symmetric players get the same. If a person is a dummy, he gets 0. After having defined dummy and symmetry with care, and it has also that property of linearity. However, I don't have okay. I'm telling you what I know. There's more work to be done. And I want to now give a couple of examples of such games. So let me try to give it to you. Okay, by the way, a philosophical remark which I can't help making. Shapley's axiom, I want to recall, the words in parentheses are mine. And by the way, he wrote this in his working RAND report, working paper in 1950, but when he published it, the paper in 53, he dropped this axiom. He said, we is the game, or he thought we is the game, or he decided to call we the game. Okay, but the game, as we saw earlier, the airport problem and the landlord problem are two different games. They happen to have the same characteristic function. We suppress that time. So what was Shapley doing? We are looking at games, we compute its characteristic function, and then we say, all right, we can ignore the other details of the game and just go to the characteristic function and figure out how to divide the cake there. Because the division of the cake should be the same for all games with the same characteristic function. That's the approach in Shapley. I am reversing the gaze, looking back, and I'm saying, given an abstract thing called the characteristic function, maybe we can find a game which comes from which the V comes, and maybe we can find a game which is transparent, where the solution leaps to your eye. And so the game I found was this representation of identical planes using airports. Okay. Okay, so I have to say that this is I didn't know of Shapley's axioms, by the way, this axiom, till after I had written the paper, but I'm glad I found it. Wanted to refer to him. And here are two examples that I want to end up with which give rise to incomplete coalitions. First is very simple. There are 5 parties left to right on a political spectrum. The extreme left can never coexist with the extreme right. So there'll be no coalition where A and E are together. Okay? So the extremists can only live with their neighbors. So A and B is a coalition, and E and D is a coalition. And now the B and D, which are left moderate and right moderate, can exist provided the one in between is there as an intermediary to, intermediate between them. So that's a coalition. I'm assuming that no party by itself is viable. They need a coalition of at least two. And so here is a collection. It's not a quasi-algebra, but it is the matrix, but it has full span, and the method will work in such an example. Okay. Here is another example. There are n players. Each is producing a unique output. So I can identify the outputs with the players. They send their outputs to an intermediary, a retailer. The retailer can bundle the outputs and sell packages. So the retailer forms a partition and sell pieces of the partition. Okay. Now, how much, I didn't write it, but how much, so he makes a partition, how much each piece makes depends on where in the partition in which it is embedded, okay? Because if I make a package and try to sell it, it may be competing with other packages I have made. So how much a package makes will depend on the other packages in that part. This is called games in partition function form. That's the idea. So we can define certain partitions are feasible, but not all partitions are feasible. For example, if you are selling a car and the market is India, you can't sell a left-hand drive car and a right-hand drive car together. They can't be in the same package. Okay? So I leave it to you to think of examples where certain partitions are not feasible. So let's say some partitions are feasible. Now, how much money, how should I define a game? Well, first, given any partition, I can look at the algebra that it generates this way, because the elements of the partition are the atoms. You unite them and you get an algebra of coalitions, right? On each algebra, I can define a game on each partition, the algebra, by saying what a coalition gets is, it is made up of a union, right? So it is, these are the atoms, it's made up of them, so it makes it this way. This could depend on the partition itself. I should have put a P there. And the union of algebras is not an algebra, but it is a quasi-algebra. So our theorem will apply, and we can now define a game as follows. So I have a collection of coalitions. The domain has become clear. It's a quasi-algebra. Therefore, it has full span. Quasi-algebras are a very small subset of full span. And I can define now V of S in multiple ways. One is, if a coalition forms, it has no control on how the players outside will split themselves. So being cautious, it looks at the worst case for itself. Or it can go even further. This is a being pessimistic, but not too pessimistic. It can become very pessimistic and say, if a coalition forms, it imagines that the others will find a partition among what is feasible to make it as bad for us as possible. The others won't be passive. They will react. And so then you can define another V. The point is not how you define V. The point is the domain of V. And the domain of V here is the quasi-algebra. And now we know how to split. So the retailer will pick a partition which maximizes the revenue. He has to now part with it to the people who supplied the inputs. And we don't have a game in Shapley's sense, but we have a game with incomplete coalitions now. And we know how to split it, and that's it. The method that I have described comes into use here. Okay? So I am seeking. So now I ask for help from all of you. As I said, the Shapley value became a sleeping beauty for a long time. A lot of us here worked and our PhDs on the Shapley value or learnt about it. It then became a sleeping beauty. A Prince Charming has woken her up. The Prince Charming is big data analysis, machine learning, and things like that. And I showed you on my second lecture the long list of applications in healthcare, blah, blah, and especially in machine learning. Reams of papers. I just Googled and got a huge list, okay? And Professor Mullan can tell you more. I'm hoping he'll send me something so I learn also about it. It's a lot in use. However, I do think there are situations in these contexts where all coalitions cannot be thought about, that incomplete coalitions will have a natural role to play. And the reason I'm not even finishing writing the paper is I'm waiting to succeed in finding some applications, okay? But this is where I am at the moment. So this is very much work in progress. Any thoughts you might have will be very helpful, and I seek feedback. Okay, so this is the first half of my lecture today. How much time have I used up? Because the second, I'll ask all the senior colleagues of mine to please feel free to leave, because what I want to now talk about, since this is a game on cooperative game theory, but you know, as we saw in two-sided matching and we saw in kidney exchange, it's meaningless to split cooperation and non-cooperation. In both of these, we had to look at dominant strategies, you know. We should call it topics in game theory. This artificial division of cooperative and non is so stupid. But anyway, today I want to discuss how, through non-cooperative behavior, in a repeated game, if there is enough long horizon, you can get cooperation. So I'm going to talk about the folk theorem, especially in the context of prisoner's dilemma. And I don't want my senior colleagues to stay here because they know all about it. So please go. Okay, now I'm switching topics. We'll take a 1 minute break. Yeah. I have 23. That's enough to tell you the folk theorem for prisoner's dilemma. I'm going to do that. Huh? Thank you. You are most kind. Okay, we are having a breather. And this is, I'm going to, this is, oh, what happened? This is from a course I teach, both at Stony Brook and Yale, and I'm going to skip a bit of it, though it's very interesting. And I want to describe to you the way we model games, or what is called with strategic or extensive form with incomplete information. So I'm going to just tell you how this game is played. Player one starts. The first move has to be made by player one. He can choose one of three moves. You see, the language is coming from chess. Huh? Players make moves, right? So this person can choose either E or F or G. If he chooses E or F, then it's two's turn to make a move, but he won't know whether the guy has chosen E or F. So we pick a big balloon, and he has to decide what move to make. It can be A, that means both places A, or B, both places B, or C, because he doesn't know which place he's in, okay? So he can't choose to do A in one, he can't choose to do A in one place and B in another. He doesn't know where he is. He has to take an action without knowing. So lack of information forces him to make the same move. And you see over here, if he chooses, so now in this case, Mr. 3 has to choose either alpha for both places or beta for both, because he doesn't know the history of how you got there. So these are called games with incomplete information, okay? And to define the game, we now have to talk about strategies. So what is the strategy of a player? The strategy of a player is to decide what to do at every information set that he could be in. Yes, so that's what it is. You know, in chess, a strategy is very complicated. It's a game of complete information. Chess is a game. What So when people make moves, we are not talking mixed strategies. When people make moves, you get a play of the game. You go from start to the end, and at the end there are payoffs written. Okay. Strategies are a contingent plan on what to do at every information set where you might have to act. And so chess is a game. What happened between Fisher and Spassky, when you saw the board, is a play of the game. Strategies of Fisher and Spassky, something else. That is a plan in the mind which they never had, because the size of the game tree for chess is more than all the molecules of the universe or something. But anyway, but theoretically, a strategy of Spassky would say, if Fisher had done this, I would have done that. If he did all counterfactuals, which never happened in any play of the game. So I hope it's clear to you what a strategy of a player is. And the outcome of a strategy is a play of the game, what happened between Fisher and Spassky. That was with perfect information. All right. It's easier to talk about it than to draw it, but I had some... yeah, I'm doing the folk theorem for prisoner's dilemma, but you are welcome to relax. So I'm going to discuss the prisoner's dilemma. So I'm going to discuss the prisoner's dilemma, which is given here. There, you are all familiar with it. And so there are some payoffs. So I want to discuss the prisoner's dilemma played many times. So first we'll do it finitely many times, okay? And so how should we describe the game? Here is the description. They both move simultaneously. And I'm telling it to you in words. They move simultaneously. Then they find out what both of them, what the other player did. They remember what they did. So they know which end point they have come to, and then they play it again. And you just keep grafting the tree forever. And let's say they play t times. So in each time period, the players earn money. So they get a stream of payoffs, a finite stream. And they have to now say, how should I value the stream? So this is a discounted sum, or they could take, delta could be one, they could be taking a total sum or average. And that's one way to define payoffs. And there is a theorem which most books prove wrong. Don't write the correct proof. The theorem is that if the prisoner's dilemma is played finitely many times, then at any Nash equilibrium, the only play of the game, outcome of the game, is non-cooperate, 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 non-cooperate. It's trivial to see this if it is subgame perfect. But it's true for also non-subgame perfect, and nobody writes the proof correctly in the textbooks. Shocking. They somehow think only perfect equilibria are equilibria. Shapley gives beautiful examples of why imperfect equilibria should make a lot of sense, but we won't go into all that, okay? So that's a fact, you can prove it. I want to look at an infinite repetition of the prisoner's dilemma. Now we will get an infinite stream of payoffs. And how the question now really arises, how should we evaluate the stream of payoffs? Okay, when people pick strategies, it'll define an infinite play of the game. And as you move on the play, there will be payoff in each period. And so each player will see an infinite stream of payoffs. How should we evaluate it? Well, one is a discounted sum. You have some discount factor, delta. But we also want to somehow think of players who are patient, who don't care only about the short run, but who care about the long run. So we can make the discount factor go to 1, or we can make it even equal to 1 and say that you are looking at the limit of the average payoff. Okay, so this is modeling patience. And here is a theorem in sharp contrast to the finitely repeated prisoner's dilemma. In a finite repeated prisoner's dilemma, as I said, any Nash equilibrium play, whether the Nash equilibrium is perfect, subgame perfect or not, gives rise to a play where people choose not cooperate all the way. All right. Let's take that on faith. Trivial to see under subgame perfection, a little less trivial without it. Uh, but with infinitely repeated prisoner's dilemma, provided you are sufficiently patient, provided that delta need not be 1, but is sufficiently close to 1, I'm going to show you that there is a Nash equilibrium where cooperate can happen all the time. Okay, this is also non-cooperate is an equilibrium. Okay, so repetition, I'm now slightly changing Bob Auman's famous sentence. Repetition, and which means infinite repetition, patience, which means delta close to 1, enable cooperation, but they don't ensure it. Many other Nash equilibria exist. So let me describe them to you, a bunch of them in such games. And so the reason I'm talking about this is how cooperation can arise from non-cooperative behavior. Ehud, would you like to add some? No. So this is just describing everything, which I said before, for any finitely repeated. So this is a quick survey. So here is I'm describing an equilibrium, and it's very easy to say it in words. It's the way that I'm describing a strategy of each player in the infinitely repeated game. And it's like this. The players have said, I'm going to play C, cooperate. And then I'll see what you do. If you also played cooperate, so let's make a plan, quote unquote, where we'll cooperate all the way. And I, at any time, look back and see, did you stick to the plan? Then I'll continue with the plan. I'll cooperate again. If at any time I see that you broke away from the plan and not cooperated, then from then on out, I'll forever play non-cooperate. This is a strategy that both players can submit, and I say that it's an equilibrium, and for sufficiently small delta, sufficiently patient players, when delta is sufficiently close to 1. And the proof is very trivial. If a player deviates in period t, you'll have to remember this matrix here, right? So this one. You have to sort of remember it, but I'll tell you what it says. The idea is very simple. If a player deviates in a certain period, he will gain right away in the period. He'll gain 11 minus 6. But after that, he will lose 6 forever, because I'm playing non-cooperate. If you non-cooperate, you'll get 6. If you do something else, you'll get even worse. So you'll get 6 from then on out. So your net gain is 5 now, and then for the future, a loss of 6, right? And you can see that that's negative. If I've computed what the delta has to be, it has to be at least 5 over 11, and then a deviation makes you worse. So for all, so I repeat the idea. And by the way, there are many other equilibria. We can make a different plan. The plan can be, we'll cooperate for 2 periods, then non-cooperate once, then cooperate for 3 periods, then non-cooperate twice. We make a plan. And by the same punishment of playing, if you deviate from the plan, then I'm going to punish you. You get lots of equilibria. There is a whole bewildering welter of equilibria, and one of them leads to cooperate all the time. At the other extreme, there's non-cooperate all the time. Things in between are cooperate half the time on average, cooperate 3/4 of the time on average, and so on. And so lots of equilibria. It's called the Folk theorem. I'm not going into the technical details, but that's the idea. We could have done something else here. We could have said, if you stray from the plan, I'll punish you. And if I don't punish you, you punish me for not punishing you, and so on. We don't have to do that in this case. Sometimes you might have to do things like that. Okay. Another example which I like, so this is enable cooperation. I like this game very much. It's called, you scratch my back, I'll scratch yours. Reciprocity. Goes like this. Here there are, the equilibrium in this game is very bad. It gives 0 to both. However, if they could somehow alternate between 11 for one and 2 to the other, alternate, they would all be much better off. You see, that is scratching. The guy who's scratching is getting -2. The guy who's getting scratched is getting 11. Yeah. So we should alternate scratching each other's backs if we could. Can we ensure it as a play of the infinitely repeated game? So we want to create strategies. Yeah. And the idea is the same, that we'll make the plan of playing this, scratch my back, you scratch yours, the pie. That's the plan. We want to see that plan. So we'll start playing according to the plan. And each player's strategy says, if you don't follow the plan at any time, I'm going to play A forever after that. And that will also be an equilibrium if people are patient enough. You can check it yourself. Same idea. Okay. So we, as I said, to have called this course topics in cooperative games was a huge misnomer. There's nothing called a cooperative game. We saw matching, where the cooperative solution was core or stability, but we had to think of non-cooperative, namely incentive compatibility. Otherwise, we couldn't. It was a meaningless discussion. Same with kidney exchange. Same here. So I think the whole idea of a schizophrenic divide between cooperative and non-cooperative is quite bad. And it's time that we looked at models which involve a mixture of cooperation and non-cooperation. I've tried to give some examples. And Ehud, I'm very sad. I talked about a new way to think of the Shapley value before you came, where you can discuss games where not all coalitions can form, games with incomplete coalitions. So I'll have to unload that on you separately. Okay, and with that, I think I want to end this mini course. We may have a few minutes left. What's the time situation? I think we can just chat or take a break, longer break. Okay, so I'll post everything except my paper on incomplete games with incomplete coalitions and how to extend the Shapley value there, because I'm still writing it and waiting for your feedback. Okay, so please feel free to write to me if you have thoughts on that. So I'm not posting material on it because I haven't written it. Okay, I have these lecture notes. I can post those. Okay, thank you for coming, and that's the end, folks. Oops. If I'm not mistaken, the next talk here is after 27 minutes, correct? Huh? Is that right? Okay.
Good. Getting my slides on. Oh, all right. No, this is a.
Is that one?
Yeah, that's the one.
Oh, okay. I will put it in downloads. It's checking.
Yeah, that's him.
Okay, if you press F11.
11 is
Oh,
what?
no. Oh, F11 doesn't work here, but it's work, okay?
Okay.
There will be someone here to help you.
Very good. And there's a clicker.
Yeah, let's test it. Presentation mode. 80.1.
No, so the clicker is not so.
Have to put it on. Oh, okay. It is working.
Good. All right. Great. All right. I should be ready.
Okay,
Great. Thank you.
you're welcome. Não tem. Se não tiver aí, não deve ter. A próxima plenária.
A próxima terceira eu Wilson online e Roth. Aí depois é do Roth e o Untitled Chapter.
Tá. Eu vou deixar as dúvidas aqui. Ver as dúvidas. Eu vou devolver o slide para você. Peguei. Laser de pergunta.
Freeze. Qual sala que é? Qual sala que é aqui mesmo? Nem estava logado. Pô, que teste você tem que fazer do som aqui? Eu já frisei aqui.
Teste. Ah.
Som. Corta o som. A música. Música. A música só. Só a música. Som teste. Ei, teste 2. Ei, a. Ei, teste. A. Som, ei. Som, ei.
Ah, não, tá na tela.
Oi?
Tá na tela. Tipo,
Não,
aqui
então,
apareceria.
esse aí que eu tava falando, lá vai aparecer. Não, então, esse aqui foi o.
Fez o agendamento,
É,
ele enviou o link pra ele.
Ah, ele já tem o link.
Que eu saiba, sim.
provavelmente.
Hi, Bob. Can you hear me? So I can't hear you yet. You might be on mute. No, I still don't hear you. You should try speaking in Portuguese. I don't. So I'm not here.
Mr. Robert, you are muted.
He's muted.
Yeah, he is.
Bottom left, tell him that in the bottom left corner.
Yeah, please do click on the bottom left audio icon, please.
Oh, I heard something there.
No, he's still muted. It's off already. No, but yeah, I can. Yeah, I'll do that. No, actually, it asked for his permission.
Abre o microfone dele.
Eu não consigo abrir, eu pedi para ele.
Can you hear me now?
Yeah, we can. A little.
Oh, actually, it asked for permission.
Try to say something now. It looks like we should hear you now. You have to say something.
You hear me now? Yeah, we can. They says press something.
Okay, I think we hear you now.
No, we can hear you now.
Okay, I'm going to introduce you, and then we'll hear you when you talk. Okay, so it's my great honor to introduce Bob Wilson, who was my doctoral advisor. In the publicity.
Yeah.
Can you hear us, Bob?
Yeah, we can. Says press something. Okay, I think we can hear you now. You can hear me?
Okay, I'm going to introduce you, and then we'll hear you when you talk. Okay, so it's my great honor to introduce Bob Wilson, who was my doctoral advisor. And the publicity. And
Can you hear us, Bob?
we have another
I can
audio
hear
problem,
you.
Bob. We're hearing my voice again with a delay from your side. Can you lower the volume of your speaker?
Okay, so it's my great honor to introduce Bob Wilson, who was my doctoral advisor.
Just a minute. I guess he has YouTube opened.
And we have another audio problem, Bob. We're hearing my voice again with. Okay. This is. So.
Robert, did you have YouTube opened? Okay. Can you hear us?
Let me try again, because I didn't hear any feedback now. Okay, I'm going to very briefly introduce Bob Ullman. In the
advertisements for this conference, there's been a lot of emphasis on Nobel Prizes, and Bob is unusually distinguished by that measure, because not only does he have a Nobel Prize, but 3 of his students have Nobel Prizes. So he's a very effective teacher, and I urge you all to listen carefully despite the audio problems that we're having. Bob, it's all yours.
Well, I don't think I can do a thing because you can't hear me.
Yeah, we can hear you. Robert, can you hear us? Now I couldn't hear you. Did you change anything?
Can you hear me now?
Now I can. Robert, can you hear us?
Yeah, I can hear you.
No, we can hear you too.
So it's a matter of the microphone. I've got 4 different microphones here.
But we can hear you now.
Right now I'm using the iPhone microphone. I could use this.
No, we can't hear you again.
Try this one.
No, it's working now.
Try this one.
It's working. We can hear you.
To prepare for this, I did 2 Zoom sessions with my co-author, Hari Govindan, and it worked fine. So I'm...
No, we can hear you. You can go ahead. You may start.
I hear the ringtone. Oh, you can hear me now. Okay, now.
It's quite a while to do. Robert, what's the problem, Robert?
Yes.
Do you have any issues right now? Can you start the presentation?
Okay, can you hear me now?
Oh, yeah, we can.
Okay.
We can hear you.
Okay.
Please open your chat. Open your chat, and you'll be able to see the messages.
Okay, 11 of them, yes. Okay, begin, all right? Okay.
I think they can hear you, honey.
Can you hear me?
Yeah, we can. We can.
Can I hear you too? Let's go ahead.
Yeah, let's go.
Okay. Well, so I'm just going to switch to my slides then in that case. Okay, so this is the title we have. The main examples are going to be about reciprocal relationships and partners. And the technical innovation is going to be adaptive recall. So it's a bounded recall, bounded retention of memory. You see here below the abstract that that you have in your set of materials. Okay, it's just since we lost a bunch of time, I'm going to move right on. So the example I was going to give includes first of all, just sort of simple examples of partnerships, with cooperative outcomes usually. So in the case of marriage, my wife and I exchange little favors for each other all the time. So this is a gift-giving relationship. It doesn't cost me nearly as much to benefit her as the benefit I get if she reciprocates. So the famous example on Wall Street in the financial markets is the repo market for overnight loans. In this case, the borrower offers a repurchase price tomorrow for a treasury bond that's offered in the security that the lender buys today. So they just keep doing this. They have these overnight, it's just an overnight loan. Each party gains because the lender earns an interest overnight on the loan he's made, and the borrower can use the money during the night for whatever purposes they have. So in the repo market, you have these borrowers and lenders doing this repeatedly, day after day. The thing about game theory is that it's an embarrassment on this subject because it's the folk theorems say, well, anything can happen. There's no particular reason why they should have cooperation. In fact, you might have none at all. And subgame perfection has a certain ridiculous quality. It says the person who deviates should be punished, and then the person who fails to punish the deviator is to be punished. But of course, in a dyadic relationship, that's going to be the original party. So it seems like game theory is this very weak tool. And the folk theorems are very disappointing. They seem to say game theory really doesn't have much to say about long or repeated relationships. So let's talk about the game. We're going to talk the stage game. This is the game that's going to be repeated. So just to summarize it quickly, the player one, say, can do a favor or not for player two. It costs something to do the favor, and doesn't cost anything to not do it. So when we talk about the benefit that he gets, this is not the benefit. We're not comparing his cost to the other party's benefit. We're talking about his cost and his own benefit if that favor were reciprocated. So this is just the prisoner's dilemma with alternating moves. So here it's described as a Stengel version of the prisoner's dilemma, because player one moves first and player two's responding. But of course, in a dynamic game that's repeated, then I'll just summarize it. On odd days, player one's choosing to cooperate or not, and on even days, player two does. We're talking about without discounting. So in that case, we're interested in the long-run average payoff. And the Folk theorem says that any non-negative vector of feasible average payoffs is an outcome of a subgame perfect equilibrium. And what we want to do is construct some sort of equilibrium selection here, something that narrows down the set of possible outcomes and identifies some equilibrium. So the method that we're going to be talking about is we're going to have a sequence of finite approximations of the infinite game, and we're going to have the criterion that their sets of Nash equilibria converge to the set of Folk theorem payoffs of the repeated game. But we're going to be making equilibrium selection along the way. So the subgame perfect equilibrium outcomes are quite different. We want to know when they will just be either cooperation perennially or converge to it. So for this kind of thing, when we say finite approximations of this game, you can't be talking about a finite horizon models or bounded recall strategies, or, by the way, which is studied by Sobel, and he proves a theorem that even with bounded recall automata, then the subgame perfect equilibrium there's a Folk theorem, in other words, in subgame perfect equilibriums. So we have to do something different. And the point of the paper here is to talk about this alternative method, which is adaptive recall. So in this case, well, we have the description here on the screen, but let's think of it the way it is. It says if you're playing this game and you reach a period where what you remember is exactly what you remembered at an earlier stage, then you should take the same action. So that's to say you're kind of an automata of a certain kind. That is, along this path, when a memory is repeated, your action's repeated. This does not imply an ordinary automaton where if the memory is the same as one could happen on a different path, then you would repeat that action. It's not of that kind. So we're going to talk about the game. We had here the game G infinity, which is the infinitely repeated game. And GK will be when we talk about the set of paths, when we have this K period memory. And for simplicity in the presentation, we assume that both players have the same memory length, that is K is the same. And also that their costs and benefits are the same, make it all symmetric, just for simplicity in the presentation. So the set of paths that you get is finite. And the reason for that is that as you proceed along any path, there will, in finite time, you reach a cycle, and then from there on, you cycle. And so the payoffs of the infinite path are determined in finite time for every path. And then, in particular, there's a well-defined sense of subgame perfection, because if you go out to a node where a cycle, the first cycle is closed, you would look at those are, think of those as the terminal nodes of a perfect information game. In each case, the payoff that's assigned at that node is the continuation value along the path generated by the cycle. So you can work backwards from the nodes where the cycles close to compute a subgame perfect equilibrium. So it's a very simple, well-defined concept here for a perfect information repeated game. It gets more complicated when we talk about imperfect information and other players and all kinds of other complications. But for what the context we're talking about today, it's just very simple and straightforward. So what we're proposing then is a selection, equilibrium selection. And the way we're going to do it is have this selection of a game. The finite game is a finite selection from the repeated game. So its paths are a subset of the paths of the original one, and you cannot distinguish them, etc. So in this, it's an intuitive sense that you would imagine. So we say that a sequence of finite selections of the games, approximating game, approximates the infinite game if the Hausdorff limit of the set of their Nash equilibria is a set of Nash equilibria of G infinity. That is, it's the Folk theorem set. So adaptive recall that we've just defined a few minutes ago, what it does is yield a finite set of paths. So the game's finite, and their continuation values in finite time. So as I mentioned in the previous slide, it's a finite game, and we can compute like subgame perfect equilibrium by just backward induction. So this is an example of using a refinement. It could have been more fancier refinements than subgame perfection, but this is all we need for this example. And then you ask the basic questions of this method, of applying this method, which would be under what conditions on these approximating sequences of games, and the refinement that's used on their equilibrium outcomes. When will it converge to a set of efficient payoffs, which is the sort of thing that we're really interested in? And question two, when's there a unique outcome? Well, of course, for what's going to happen is, first of all, that there will be a Folk theorem for these approximating games for the Nash equilibria. So this next slide here is written in terms of 2K, assuming each player's memory retention is 2K, so that there's an even number of periods where they alternate, so each has acted K times. So we can think of the memory at a given point in terms of the frequencies with which during the frequency of cooperative behaviors during the memory. So we just get a representation as a point in the unit square, and these outcomes are just cycles well, they're paths that then start cycling. And there's a little theorem here that I'm not going to go into given the time, but that you get a full theorem here for just for these approximating games. But the subgame perfect behavior is completely different. Generically, if this benefit cost ratio, P over C, if it's an irrational number, then there exists a unique subgame perfect outcome called X star of the approximating game with finite recall. So there's a little proof here, but it's very simple. Why is it? What's the role of irrational numbers? We're just saying that it's a generic condition, and it comes about because if you compare two paths, X for players I and J and X prime for players I and J, and you say, well, suppose we're indifferent about which choice to make. Well, that would imply if B over C is irrational, that doesn't work out because these X and the X's are all rational numbers. So it must be then that this is just a general result about perfect information games that if there are no ties, then there's a unique subgame perfect equilibrium. So this is a very familiar result. And you can use it too, it's pointed out here, for finitely many outcomes numerically. So we'll be using that argument implicitly for other finite approximations, like those that with adaptive automata or pruned versions of the game or so on. So the principal simple theorem is first that that the purely non-cooperative outcome is not a subgame perfect outcome. And I'm not going to spend time on that, but just point out that the nature of the proof is to consider perturbing the game by a tit for tat strategy. And in that case, party has an incentive to cooperate in order to get the reciprocal action with some probability by the tit for tat player. Okay, so now, when one puts this apparatus to work, the first thing we did was do computations. And for K up to 4, in fact, for K1 and K2 less than equal to 4, and a range of benefit cost ratios, everything from 3/2 up to 5. We get a benefit that the outcome is the 1-1. That is, the frequency of cooperation is 1 in every period in the recalled memory, and it's also then the frequency of cooperation along the path. So, well, we can't prove this in general, we found, except it seems to be extremely difficult to prove, because the game is finite, but its size is increasing exponentially, and we don't have access to any recursion that could simplify it. So now we're going to talk about an approach that's been successful. So if you take that finite game, GK, you realize that it has lots of nuisance data in there, a lot of noise, because, for example, that says if in that game, when you talk about what a memory is, it's a memory that includes a specification of the actual pattern of cooperation and non-cooperation over the course of that segment of memory. Well, clearly we don't. Your payoffs from this in this problem, the players' payoffs don't depend upon the pattern. They only depend upon the frequency of cooperation. So we would like to get rid of that. And so we're going to consider pruning it by selecting a subset of the paths. Now, as to follow this program, you have to have that the set of Nash equilibria is still converging to the Folk theorem set of payoffs, but there's a unique subgame perfect equilibrium for each K. And you just require for this that the players take the same action at two nodes that have the previous memory, they have the same empirical frequency. So we can think of this as a game that's played by frequentist automata, and their states are represented in the unit square in terms of these grid points. Okay, so we could think of these, when you look at these games that you get that way, we get, well, the two I'm going to describe are ones that have a bargaining interpretation. So let's take the first one, the simplest one, which is has a more severe, quite severe pruning. So we're, as I mentioned, we're getting again a game where the paths are on the grid in the unit square. Again, I'm using 2K so that each player moves K times, and finally after K actions by each player, initially that establishes a frequency called X that is the starting point in the grid. Now it could be X is 1, 1, so it's up there, that northeast corner, it represents cooperation. And along the diagonal, they both cooperated the same amount of time. If you get a point above the diagonal, that's saying that player 2 has been cooperating more frequently than player 1. Now remember that benefit that cooperation is costly, and if the other player is not reciprocating, then player 2's actually put himself in a disadvantage because player 1's not reciprocated. So in this, on the grid, the player 1 can move to the left or right or stay put in this selected game. And if the way this one's set up, if he stays put, then the game is over. So that's to say that if he sees that the continuation path, which is, remember, we've reached this, if he stays put, then that creates a cycle, closes the cycle. I haven't explained that, but I'm going to jump over the point. And but if he likes the continuation value, then he just ends the game. So you can think of it as the players alternatingly making proposals. Say, well, here's this point that we're at, but we can move a little to the left or right, says player 1. Player 2 says, well, we could move up or down a little. And if either one says, well, I want to stay put, then the game is over. And the game ends when we get a cycle of that kind. So the second variant is one that I like better. That if one player stays put, then the other player also has to stay put to end the game. So that's a real bargaining context. It can't be that one player ends the bargaining. It's that they have to agree. Okay. So the theorem is the unique subgame perfect outcome of the game played by the bargaining automata of the kind I just described that are the frequentist type it's 1-1. It's perfectly cooperative. And I'm going to skip over this one and talk about the second variant down here at the bottom. So there's this interesting property that's proved. It's a long technical proof, but if you're at a point in the grid, the subgame perfect continuation cannot be Pareto improvement over what you've got already. Well, what does that say? It says you can never make both parties better off. All you can do is move in a way that makes if one gets better, the other has to get worse. And in fact, what happens is the subgame perfect path, I wrote here, slides toward the diagonal, and then when it gets to diagonal, it stops. Either party wants to change. So you wind up with a equal amount of cooperation, but you're on the diagonal possibly below the perfect cooperative point. So what does this imply? Well, that says this is what happens for any point of any pair of frequencies of cooperation that you arrive at after the first 2K rounds that establish the initial point. Well, so which initial point do you want? Well, okay, so that's just a trivial little proof that then says, okay, in doing those first rounds, what both of them want is to establish a point of perfect cooperation. So in the first 2K rounds, K actions by each player, each cooperates. So in the grid, they start at 1-1 and they stay there. And that's the end of the game, and it's a perfectly cooperative subgame perfect outcome. So this is obtained, this kind of result you get by selecting among the paths. So we started with an infinitely repeated game, and we selected these finite representations based upon adaptive recall. And then we found, well, okay, there's a lot of junk in memory there, like for the very temporal pattern of cooperate and defect. So we get rid of that, and we can select further and further. And amazingly, you can make very severe selections so that you get that is simple enough to actually prove the result. And the implication from the previous analysis then is, I have a infinitely repeated game, but it's approximated by this sequence of finite games, which are generated by adaptive recall. And in each of those, there's a subgame perfect equilibrium of cooperation. So we're, I don't know how you put it, we're proposing that this is select, therefore, cooperative behavior as the path of the infinitely repeated game. Okay, so now my time's not completely up, but I'm just, we have these concluding remarks. I'm sorry the time got cut so severely short by my audio problems. So there's this summary points of the conclusion. Why is it we sometimes don't expect uniqueness of the outcome in repeated games, like a folk theorem? And one is that, since there's no commitment, all kinds of the future is always open possibilities, and the past is not restricted what could happen. And the other case is that you have simultaneous moves that creates a coordination problem. Well, what we're doing here in this methodology is to use adaptive recall and associated finite selection of these games to mitigate problem one. That is to say, the actions do combine some degree of commitment and signaling, because what you've done before puts a constraint on what you can do in the future. Just through this requirement that if your memory is repeated, then you'll repeat your behavior. Here, the problem two about the simultaneous moves, I say if the stage game is sequential, I should say, that they alternate actions, then you don't have a problem with simultaneous moves and all the problems that brings. So the subgame perfection works in a very, very simple game like this. But more generally, you can then apply as a equilibrium selection of infinitely repeated games, ones with all these folk theorems, certain concepts, and we mentioned essentiality, that is to say that it's a component of positive index, or stability. I mean, there are all these are to have technical definitions about what we mean by stability. But there are various these equilibrium selection criteria. So to summarize, strategic players who interact repeatedly communicate using a rich but finite language. They do not talk over one another, then they must necessarily reach an efficient outcome. Well, that's a that's a boast. It's too expensive, of course. But anyway, the thing is that for the simple class of games, this reciprocity game, it works. Okay, so I guess I'll stop sharing. So we should have, if you have questions or discussion from the audience, because we have a few minutes. Guess not. Okay. I'm aware that you guys are going on a picnic and a barbecue, and I thought you'd run out of the room when this is over, so that you'd be for these afternoon activities. Well, have a good time. It's a pleasure to talk with you. Okay. Bye.
Okay. All right. Well, Marilda appears not to be here, so I'm stepping in to introduce my longtime colleague, Al Roth, who told you that Bob Wilson had 3 of his students win Nobel Prizes. He didn't mention that one of them was himself. So it's a pleasure to have Al here. Al is one of the economists I admire most in the world. I mean, the work that he's doing is actually saving lives. The work on helping to develop the kidney exchange, as we all know, isn't just an ordinary market. It's one that every time those transactions are made, lives are being saved. So that's about as important as the work any economist does. Anyway, but Al has done a lot more, and I don't want to take up all of his time. We've seen what happens when you waste too much time in the introduction. He's done a lot more. He and I taught what I think was the first course in market design in the year 2000 together at Harvard, so I've known him for a quarter century. Actually, he also taught me in graduate school, so I've known him even longer than that. It's my great pleasure to introduce Alvin Roth.
Thank you. Sure. I'll use that.
All right.
Brazil slides. Great. Yeah, that's good. Thank you. Thank you. So it's true, I've known Paul for a long time. He took when he was a graduate student, he took a class from me. That was 50 years ago when we were both around 4 years old. And black markets and market design. So this is, you can't hear me. Can you hear me now? Okay. So my talk's going to be a little different than some of the talks we've heard up till now, because in Bob's talk just now or in Roger's talk yesterday, yeah. So one kind of talk we have in a game theory conference is looking in more detail at a game and trying to learn more from its structure by refining away inessential elements. So we heard some talks like that. My talk's going to be the opposite of that. Market design is the engineering part of game theory, but it involves looking at options, strategies, players who may not be within the original game. So rather than focusing more and more on a particular game, we find ourselves looking outside the game and seeing what kinds of things might influence it. So that's why I'm going to tell you about some things that are outside of the formal structure of the games that I'm looking at. Now, to give you some background on this, Marilda and I wrote a book on matching in 1990, and this photograph is from a conference at Duke to celebrate the 20th year of the book. That was in 2010. So we're coming up on 40 years, and Marilda, who isn't here right now, asked me to remind you, in case you're doing the mental arithmetic, that we were both around 15 years old when we published the book. One of the interesting things about matching theory is it combines what used to be thought of as separate parts of game theory, cooperative and non-cooperative game theory. So for those of you who have been listening to Mike Ostrovsky give a short course on matching, you know that Gale and Shapley have this famous result that says for simple models of matching, a stable matching exists for every marriage market. And that's part of what used to be called cooperative game theory because it's a coalitional model. It says a matching is stable if there isn't a blocking pair of two interested parties who would like to get a different matching. It doesn't tell you the detailed strategies that they might use to get that different matching. It just lets you know that there aren't going to be any such blocking pairs, so maybe you don't have to worry so much about how they will search for ways to get a different matching. But the non-cooperative game theory focuses on strategic behavior, and there we have theorems that say whether or not you can make it a dominant strategy to reveal truthfully to a mechanism that will give you a stable matching, things like that. And in general, it's hard to find dominant strategy mechanisms, but what we can do in matching is we can, in simple matching problems, is we can make it a dominant strategy for some of the players to reveal, to behave straightforwardly. So Demange, Gale, and Sotomayor have a general theorem that allows the other results to be proved about that. So that's a combination of cooperative and non-cooperative game theory. I'm going to tell you a little more about that and why that's so useful and such a useful approach in market design. Okay, so in 2015, I wrote a book for a general audience on market design. It's been translated into Portuguese, incidentally. And one way to think about market design, and one of the ways we tend to think about it in a game theory conference, is that it's motivated by mechanism design. And mechanism design is the very game theoretic idea that if you have players whose types you can't observe, but you have some desired outcomes for getting. You have desired outcomes that depend on the types, like you would like an auction to be efficient, you would like it to be won by the type that values the thing being auctioned the most, then you can define a game that they will play whose equilibrium will give you the desired outcomes. And so in mechanism design, the theorist takes on a very godlike role of designing the whole universe that the players will inhabit. That is, the players can do nothing in the game but choose one of their strategies, and then we rely on them to choose their strategies thoughtfully in a way that will give us an equilibrium that produces the desired outcome. But market design is a little different than that, and maybe a better name than market design, if Paul and I had worked harder at the beginning of the discipline to get a good name, maybe a better name would have been marketplace design. Because what we're designing when we design what we get to design is not the whole market, but it's a small part of the market. So here, before I showed you a picture of the mechanism taking up the whole screen, but what we get to do is we get to design a mechanism that will be a small part of a larger market, right? So when you design a mechanism, a matching mechanism, for instance, to assign doctors to their first jobs, doctors were already getting their first jobs before the clearinghouse was designed. So they have other strategies that they could employ. They could go back to using the old mechanism to get their job. They could have negotiations offline with the employers who might employ them. There are lots of other things they can do. And so one of the things that the marketplace designer has to do is tempt the market participants to participate in this marketplace, right? And that's where the combination of cooperative game theory and non-cooperative game theory comes to the fore. That is, in designing the behavior inside the marketplace, the mechanism, we're mostly thinking about strategic actions. What strategies can they employ? Will they reveal their preferences truthfully? Things like that. But out in the big market, they have strategies we can't even see. They could call people up on the telephone and have long natural language conversations. So the strategy sets are enormous. But if there are no blocking pairs, then the incentive to circumvent the marketplace will be much less. If there are blocking pairs, even though we don't know how they might circumvent the marketplace, we know they'll have an incentive to try. They'll be trying to find each other, and their strategy sets are large, so maybe we can't stop them from finding each other. And that's why we focus on, in the strategic game, getting equilibria that produce stable matchings. That helps us defend against all the strategies we can't see in the larger market, where people, if they were incentivized to look for strategies, might find ways to circumvent the market. Okay, so my most recent book, just came out this year, is a different sort of book. The first book, Who Gets What and Why, the second of the book I showed you, the Who Gets What and Why is sort of an optimistic book about market design. It says sometimes markets are broken and we can fix them, and that's exciting for economists. This book is less optimistic. This book says sometimes markets are broken, but it's going to be hard to fix them because we don't agree on what we want them to do. We don't agree on what would be good things to do. And this is even a more outward-facing part of market design, if you like, than standard market design, where we have to convince and coordinate market participants to adopt and implement and maintain a new market mechanism. Okay, so here's the picture I showed you just a moment ago, where the mechanism is a small part of the large market and players have other strategies. But it turns out there can be other players who we don't even think about when we make the marketplace. These other players may not even want to play in the game. They may not even want to allow you to play in the game. And they're responsible for laws and regulations that impact the market, even though these players aren't in the game. So not only do we, as market designers, not only do we have to convince people who want to participate in the market to use our marketplace and find it as an efficient place to make transactions, we may have to convince lawmakers, and we may have to try to contend with social norms held by people who aren't going to participate in the market itself. And they may shape what kinds of marketplaces can function and which cannot. And the big lesson that I try to draw in this book is that markets need social support to work well. So it's not just enough for the participants to want to do something. They have to be able to gather support from society that will make it a feasible thing to do. And sometimes societies ban markets. I'm talking in that book about morally contested transactions that some people would like to engage in and other people think are wrong to engage in. But bans also need social support, because when bans don't have a lot of social support, you get black markets when you legally ban something, and the black markets can be run by criminals, which is not always the best way to regulate a morally contested market. So those are the kinds of things I talk about. And I talk about a lot of different repugnant transactions, a lot of different markets that are morally contested. Some people think they should be allowed and some people think they shouldn't. And I'm not going to talk about most of those today. I'm going to use as my example kidney transplants. Okay, so I'm going to talk about kidney transplants, and in particular, I'm going to talk about kidney transplants in a way that is now controversial in Brazil, and where there are efforts underway by Brazilian doctors and those who try to help them to change Brazilian law about transplants. So to do that, I'm going to have to take you on a tour through that big ocean of outside the market, outside the marketplace facts and things we know about it. I'm going to have to tell you about kidney transplants, but my target at the end of this talk, the game theoretic target, is we want to change the rules that Brazilian society places on kidney transplants, because changing those rules might help save lives in Brazil of people who have kidney failure. So that's where I'm going, but it'll take a little while to get there. Okay, so let me tell you about kidney transplants around the world. Kidney disease is one of the top 10 causes of death almost everywhere in the world. And transplants are the treatment of choice. So there are transplants all around the world. And this graph tells you something about the success of the medical communities in different countries at producing transplants. And it's a metric that the medical communities like, because it talks about transplants per million population. So of course, that's a measure of medical efficiency of a certain sort. And there are blue bars and orange bars on the graph. And the blue bars are deceased donation transplants per million population, and the orange bars are living donation transplants per million population. And the reason you can have living donor transplants of kidneys is that healthy people have 2 kidneys and can remain healthy with 1. So if someone you loved has kidney failure, they're not doomed to die on dialysis, which is what will happen if they can't get a transplant, but you might be able to give them a kidney. Okay, so what you see here is per million population. Spain, in the year that I've got data for, I think this is 2024, Spain leads the pack, mostly because of its large number of deceased donations per million population, not so many living transplants. Number 2 is the United States, which has also more deceased donations than living donations, but quite a few living donations. The Netherlands are next with even more living donations per million population. I picked out Israel as number 8 because that's the first country where they have more live donations than deceased donations. But that's true in other places too. For instance, India, which has more living donations, almost all living donations. And Brazil, which you can see is here, has almost all deceased donations. So Brazil has a lot of kidney transplants, I'm going to show you on the next slide, but they're almost all from deceased donors. Okay, so this graph is organized by transplants per million population, but I've picked 3 big countries there, Brazil, China, and India, which don't have so many transplants per million population. But when we look at total number of transplants, we see Brazil is number 4. It's the US, China, India, and Brazil, because even if you don't have so many transplants per million population, if you have many millions of people in your country, you can do a lot of transplants. And scale is going to be important. So if there's time, I'm going to get to talk to you a little bit about why it might be desirable to do kidney exchange across borders. And in particular, it would be desirable for people to come to countries where there are lots of kidney transplants. So I'll come back to that, but keep in mind that Brazil, which does almost all deceased donor transplants, is one of the big countries for kidney transplants around the world. Now, the US is at the top of this list, and it was near the top of the other list. So you might think that the US is doing a great job, and that's not true. Nobody's doing a great job. Being at the top of the list doesn't mean you're doing very well. So here are some statistics from the United States to give you an idea about how poorly we are doing, and all countries are doing. In the US, we have about 130,000 new cases per year of kidney failure. Okay? And we have about 100,000 people on the waiting for a deceased donor kidney, and there would be more people registered on the list if most of them were going to get kidneys. But in fact, most of them are not going to get kidneys because we do fewer than 30,000 kidney transplants a year in the United States. Okay, so we have 130,000 people each year who could benefit from a transplant, but most of them will die without getting a transplant. Okay, because we do, in 2024, we did 21,000 deceased donor transplants and 6,400 living donor transplants. And the transplants have been going up over time. I'll show you a graph in a minute. In 2002, at the turn of the century, we were doing just 8,500 transplants a year. So transplants in the US have been going up. What's the problem? The problem is the gap between the number of transplants we can do and the number we need to do has grown. So here's the growing gap. We now do, almost 30,000 transplants a year, but have 130,000 new kidney failure cases a year. That gap has grown over time, and that's true around the world. So I'm going to tell you some stories that if I stopped too early would be stories about victory after victory in getting people transplants. But in fact, it's victory after victory in a war that we are losing. And so the need to increase the number of transplants is only growing. Okay? And it's not just a problem in rich countries. Most of the people who die of kidney failure don't live in rich countries. And so that's widely known. Okay, so as I said, there are about 90,000, 100,000 people officially enrolled in a waiting list to receive a deceased donor organ in the United States, a kidney. And when economists see long queues, we suspect that prices aren't being allowed to increase the supply. And indeed, that's the case. It's against the law to pay living donors for kidneys almost everywhere in the world, with the single exception of the Islamic Republic of Iran, which I'm not going to talk much about today, although if there's time for questions, we can certainly talk about that. So here's a snippet of the US law, the National Organ Transplant Act of 1984, which says it shall be unlawful for any person to knowingly acquire, receive, or otherwise transfer any human organ for valuable consideration. And I cut it off a little too early there. It says for transplantation. It's not against the law to pay for cadavers for anatomy research or for museum exhibitions, but it's against the law to pay for an organ for transplant. Okay, European countries have a variety of very similar laws. Here's a general statement from the Council of Europe: the human body and its parts shall not, as such, give rise to financial gain. You can't pay a donor for a kidney or the family of a deceased donor. Here's the Brazilian law. Here's a snippet of the Brazilian law. I have it here translated into English. It says, the first part says, the gratuitous donation, the donation without payment is what that means. The gratuitous donation of tissues, organs, parts of the body during life or post-mortem for transplantation and treatment purposes is permitted, right? So there's active transplantation in Brazil, but you can't pay. And, I don't read the Brazilian law as fluently as I read some others. So the place where I can see most clearly it says you can't buy or sell tissues is when they talk about penalties. So you can go to jail for paying or being paid for an organ, okay? And for being a broker, right? The same penalty applies to anyone who promotes, facilitates or derives any advantage from the transaction. And they mean monetary transaction. I'll come back to that. Okay, so here we are. We can't increase the supply of kidneys by paying donors. That's something that occurs to economists. There's been a lot of literature on this. But in fact, in 2007, when I first started writing about repugnant transactions, it was in conversation with an article by Gary Becker and Julio Elias saying that it would really be a good idea to pay for kidney donors. And what I said then is I said, that may well be true. I'm inclined to think it is. But as economists, we can't convince people of that by just saying slower and louder that voluntary transactions between well-informed parties that don't have negative externalities increase welfare, right? Because when you see something that's against the law, almost everywhere in the world, you have to suspect that there are forces at work that economists should understand better than we now do. That's the target of my book on moral economics. But that doesn't mean we can't think of ways to increase kidney transplants, taking into account the fact that it's against the law to pay for a kidney. So one of the sources that blocks more kidney transplants is you might be healthy enough to give someone a kidney, and you might love someone who needs a kidney, but you might not be able to give your kidney to the person you love because kidneys have to be well matched. So it's quite a bit more complicated than blood types, but here's a picture that shows the basic idea. Donor 1 loves recipient 1 and would like to give her a kidney, but they have incompatible blood types. It makes that transplant very hard to do. Donor 2 loves recipient 2. They have the same problem, but in reverse. So when you look at the picture, you see what we need is a blood type B kidney for recipient 1 and a blood type A kidney for recipient 2, and they're both available in this picture. So if we could exchange kidneys, then each patient could get a kidney that's compatible with them from the intended donor of another patient. Okay, so we'd get 2 more living donor transplants than we would otherwise get. And before we had kidney exchange, these donors used to be sent home, and the patients would continue to wait on the long, dangerous waiting list for a deceased donor kidney. a waiting list on which thousands of people die each year while waiting. But here we can get 2 transplants that we wouldn't otherwise have gotten. Okay? Now, you could ask, and indeed we were asked, maybe this violates the American law. Remember, the American law doesn't say you can't pay a donor. It says you can't give valuable consideration. So valuable consideration is one of these obscure legal formulations that clearly implies you can't pay money. But maybe it rules out kidney exchange. There's something valuable being exchanged here. But the US Congress amended the law after 3 tries in 2007, after 3 Congress, to say that that sentence, the preceding sentence in the National Organ Transplant Act, does not apply with respect to human organ paired donation. And paired donation is a term of art for kidney exchange that avoids use of the word exchange, which lawyers didn't like, and it says it's legal. We got this in 2007, 7 years after we had started doing kidney exchange. There was some question about whether it was legal, but no one was prosecuting American transplant surgeons who were doing kidney exchanges in the interim. For you Americans in the audience, the Norwood Act, when it finally was brought up to a vote, passed unanimously, right? No one voted against it. So there was a time when the US Congress could agree on something. And they agreed that kidney exchange was a good idea. Think how nice it would be to have that Congress again. Okay, here's the Brazilian law. And let's think about these laws, right? These are, the Brazilian law is about who can give a kidney to whom. But just as the law against compensation, both of these laws, the one I'm about to read to you and the law against compensation, are acted on, are passed out of a concern that if you could pay kidney donors, then maybe poor people would be exploited. Maybe people who were in desperate need of money would find themselves selling their kidneys and later regretting it, and that might be something we want to prevent. So in the US and in Brazil, it's not legal to pay kidney donors. But here in Brazil, there's a much more severe restriction. It says any person can give a transplant to recipients who are spouses, partners, or relatives to the 4th degree. So in Brazil, you can only give a kidney to a member of your family. Okay? Unlike in the United States, where legally you could give me a kidney or I could give you a kidney. Not so in Brazil, because we're not parents, we're not grandparents, we're not first cousins. Okay, so one reason why Brazil does so few living donor transplants is the law prevents transplants from unrelated individuals, except with judicial authorization. And judicial authorization is not so easy. Okay, so when we talk about changing laws, this is the law that I'm going to have as my target by the end of my talk. I would like to see this law changed in Brazil. Okay, but let me tell you about kidney exchange a little bit so you can see why it would be advantageous for Brazil to amend that law and why it wouldn't have to be amended very much. Remember, the concern of the Brazilian legislation is to protect the very poor from being exploited. And the way they protect them is they say, you can't get, if you just come with someone who wants to give you a kidney, we suspect that maybe you've bought your kidney and as a society, we don't approve of that. But if you come with your brother, well, that's family. What goes on between you and your brother goes on within your family. We're not as worried about that you're exploiting your brother. That's why family members are allowed to give. Okay, now, kidney exchange itself has some logistical complications. It's medically simple, kidney exchange, because you're giving each patient a kidney that is compatible to them, so you don't have to overcome their immune system's immediate intention to reject the kidney. But it's logistically complicated because when we do those kind of simple exchanges, we do them simultaneously, since you can't contract. You can't write a legally enforceable contract that says, me and my donor will give you and your patient a kidney today, and you'll give us one tomorrow. So on these pictures, you see half of a kidney exchange going on between two donors. The other half is going on, this is in Cincinnati, Ohio. The other half is going on in Toledo, Ohio. And all 4 operations are being done simultaneously. So I'm the man in the yellow gown keeping my hands out of the way. And in the bucket is a kidney. And here it's going into the man from Toledo, Ohio. And at the same time, literally the same time, they got on their cell phones and said, we're ready to go here. We've successfully anesthetized the patients and made the initial incisions. We're ready to go. Are you ready to go in Toledo? And in Toledo, Mike Reese, the important kidney surgeon, said he's ready to go. And then they did the transplant. And that way, I'll talk about that in a minute, that way no pair gives a kidney but fails to get one. Okay, so that's the importance of simultaneity. But it has the problem that to do even that simple exchange, you need 4 simultaneously available operating rooms and 4 simultaneously available surgical teams. So it's medically simple, but logistically hard. So that's going to be hard to scale up to a countrywide scale. It'll save lives, but not as many as you would like to save. And the reason we do them simultaneously is, suppose we didn't do them simultaneously. So I'm going to give you a counterfactual here on the left. Suppose on day 1, donor 2 donates to recipient 1, and on day 2, donor 1 is scheduled to donate to recipient 2, but fails to do so. That's that broken line there. Well, that really harms pair number 2 because they've had a surgery that didn't help them. And even more important, they no longer have a kidney with which to enter into kidney exchange. Right? They've given their kidney away. But supposing we start with a non-directed donor, and we have about 500 some odd of these in the United States each year now. A non-directed donor wants to give a kidney to someone and is healthy enough to do so, but doesn't have a particular patient in mind. They're willing to donate anonymously to some anonymous patient who needs a kidney. Well, now if they can start a chain in which each pair gets a kidney before they give one. So on day 1, the non-directed donor donates to recipient 1. And if, for whatever reason, donor 1 fails to give a kidney on day 2 to recipient 2, it's disappointing, but it's not tragic. Pair 2 still has a kidney. They haven't given a kidney yet. They're going to give their kidney only after they've gotten one, and so they can still participate in future kidney exchanges. And so this allows long chains to be made because you don't have to do 3-way exchange, you don't need 6 simultaneous operating rooms. To do 4-way exchange, you don't need 8 simultaneous operating rooms. And so Mike Reese, the guy who was off camera in Toledo, Ohio, organized the first long chain. And here's its picture in the New England Journal of Medicine and then later in People magazine. And the chain at the moment of this picture was incomplete. Helena McKinney, the last donor in the chain, has blood type AB. So it was a mistake for us to stop the chain, to pause the chain where we did. But 3 years later, she was still willing and extended the chain to have another 12 people in the picture. So chains can be very efficient. They can get a lot of transplants done. But they're controversial. In European countries that have kidney exchange, not all of them allow non-directed donors. So many of them just have pairwise and sometimes 3 pairs exchange and not these long chains. But chains are very important, particularly to match hard-to-match pairs. So let me give you an idea of why that's true. Here's a visualization of a data set for kidney exchange. And each node, each circle, represents a patient-donor pair. And there's an arc going from one pair to another if the kidney from the donor in the first pair is compatible with the recipient in the second pair. And what you see is there are there's 8 blue pairs, and they have a lot of incoming arcs. They're easy to match pairs. There's not going to be any trouble getting them a kidney. But there are lots of pairs that have very few incoming arcs. They're going to be hard to match, and they're going to not be able to match in simple 2-way or 3-way exchanges because they're hard to match. That is, there's only a small chance that I should say, in this data visualization, everyone, all the patients and all the donors have blood type A. So there are no blood type incompatibilities here. These are all what are called tissue type incompatibilities, which have to do with the immune system. So patients who are hard to match can be very hard to match, and it's not enough to find a blood type compatible patient. And that's why kidney exchange needs efficient scale, right? So supposing each one of us represents a hard to match patient-donor pair because the patients are hard to match, our patients, then the chance that my pair can give your patient, the patient in your pair, a kidney is very small because your patient is hard to match. But the chance I can give a kidney to someone in this big room is not so small, because even if each patient has only a 1% chance of being able to take a blood type compatible kidney, there are more than 100 people here. I could probably give a kidney to someone, even if everyone is very hard to match. The chance that you can give a kidney back to us in a two-way exchange is very small, because we're hard to match too. But the chance that you can give a kidney to someone else in the room is not so small, and the chance that they could give a kidney to someone else in the room is not so small. So if we could start a chain with a non-directed donor, we might be able to get a bunch of transplants, even in a room like this one with a lot of hard to match patients. Okay, and that's sometimes the only way to reach the hard to match patients. Okay, so efficient kidney exchange needs a big pool. And what a big pool means is steady arrivals of patients and donors. And the reason that's true is after you do the matching, right, here's some graph of compatibilities. After you've done the matching, there are no more matches left. There's still plenty of patient-donor pairs left, but there are no matches we can accomplish. Those will depend on new arrivals. And so small countries are going to have trouble matching hard-to-match patients with purely domestic kidney exchange. And I'll come back to that. Okay? So I'm not going to tell you much about the mathematics, except that, you know, we started proposing this kind of thing with top trading cycles, which many of you know about. You know, there was a famous paper by Shapley and Scarf in the first issue of Volume 1, Number 1 of the Journal of Mathematical Economics that gave us a start for kidney exchange. But now we're doing integer programs with all the constraints that we need. And those are computationally hard problems. The worst cases are hard. But we've so far been able to solve them all, although there are difficult to solve instances. These are not problems where the worst cases are hard, but all the instances you encounter are easy. Some of the instances are computationally hard. But we can find maximal weight chains for different kinds of weights that are debated, and some of them are controversial. We can find long chains. Okay? Because non-directed donors are so important, one of the things we're now exploring in the United States is starting some chains with a deceased donor. Almost 100% of deceased donations in the United States are non-directed. That is, someone dies, their organs are suitable for transplant, which only happens in less than 1% of deaths. They could start a chain, but mostly the regulations in the United States prevent this. But we're able to circumvent some of the regulations by working through the military hospitals, because Walter Reed National Military Hospital operates under different rules than the other hospitals in the United States. And in Italy, this has become an important part of kidney exchange. So that's also something to keep in the back of your minds. So here's a picture of the growth of kidney exchange in the United States. And again, if I were to stop here, you know, I would have told you victory after victory. The blue lines are the kidney exchange transplants, and the orange lines are the chain beginning non-directed donor transplants. So we have more than a fifth of the living donor transplants in the US are now caused by, facilitated by kidney exchange. Okay, so let me tell you about Brazil. Remember, the Brazilian law says you can only get a kidney from a member of your family unless a judge approves the transplant. So Stanford has funded and helped promote a clinical trial being conducted under the auspices of the Santa Casa in Juiz de Fora, that allows some kidney exchanges to happen with a judge having to approve of each transplant before they happen. So instead of just finding matches and going to the hospital, you find matches and go to court. And so far, 10 kidney exchange transplants have been done in Brazil. And here's an article in the Brazilian Journal of Nephrology in 2026, published in 2026, that talks about transplants done in 2024 in Juiz de Fora. And they say, here's a case report, kidney exchange, it's a clinical trial. We want to see if it works in Brazil, and indeed it does. So there's, a happy outcome for in a three-way exchange. But the abstract concludes by saying, nevertheless, structural, ethical, and regulatory challenges remain. This report emphasizes the implications of expanding kidney pair donation as a sustainable, life-saving strategy in Brazil. So the goal is to go back to Brasilia and speak again to the Ministry of Finance after we've got 20 transplants. Now, this was a three-way exchange that I'm about to tell you just a bit more about. Three-way exchange means you need 6 simultaneously available operating rooms for the 3 nephrectomies, recovering the kidney from the donor, and the 3 transplants. And so they say these 6 surgeries were performed in 2024. This type of simultaneous operation demands a large contingent of professionals, precise coordination, and robust hospital infrastructure. So on the right here is the team that did those 6 transplants. Standing right, so I'm standing on the far right, standing next to me, sort of crouching down, is Mike Reese. He's my hero in this story. There are 6 surgeons in the picture. There's a nephrologist crouching at the left in the front row. He's Gustavo Ferreira. In Brazil, the nephrologists run transplants. In the US, surgeons run transplants. But in Brazil, the nephrologist, so Dr. Ferreira, is the one who organized which patient should get which kidney, and the surgeons show up and make it happen. But that's a different organization in the US. Juliana Bastos is right dead in the middle at the beginning. She's a nephrologist who also was critical on this. And looking at 6 surgeries, Mike was a little worried that I would fall into the patient. And so there's a picture there of him holding me up while I balance on stools to look at the operations. And one of the fun things about market design is you get to learn a lot about the non-economists who are involved in the markets you're trying to help. And so, I'd seen nephrectomies and surgeries before, but seeing 6 in one day made me think a little bit about, supposing you were making a movie about this. There would be 2 dramatic scenes repeated 3 times each in this movie. And the first dramatic scene is when the kidney is recovered from the patient and it's carried in a little metal bowl full of ice across the hall to the other operating room, the adjacent operating room where the transplant is going to happen. So that's, the first dramatic scene in a kidney transplant. And the second dramatic scene is when the recipient's artery is connected to the kidney that's been transplanted, when the kidney starts to get blood again, and it turns from white to pink. And that's also, everyone, these guys have seen lots of these, but it's a dramatic moment. The kidney turns from white to pink, and that blood is flowing. So somebody should make a movie. Okay, so this year in 2026, in May, there was another exciting development in Brazilian kidney exchange, which is that all those surgeries that I showed you, the 6 simultaneous operating rooms, were in Santa Casa in Juiz de Fora. But there was a kidney exchange between the USP hospital and Juiz de Fora this past May, in which the donors traveled. So someone came from Sao Paulo to Juiz de Fora, and someone came from Juiz de Fora to the hospital Clínicas in Sao Paulo to do the donation. And that's, again, it was done simultaneously. So that's like that picture I showed you from Cincinnati. They're coordinating to make sure both parts of the transplant go through. And of course, to make kidney exchange a national endeavor in Brazil, it will be necessary to have lots of cooperation between hospitals. But right now, because you need judicial approval for each transplant, that puts a lot of limitations on what you can do, because surgery is fast, but judges are slow. So it's now taking, in Brazil, sometimes up to 3 months to get approval for the surgeries. And this is a real obstacle, especially for compatible pairs who could take part in kidney exchange and be like those blue dots in my data set that are easy to match, and they would facilitate the matching of hard-to-match pairs. But now, if you've got compatible pairs, sometimes they are interested in kidney exchange to get a better matched donor. But if it's going to take 3 months to get judicial approval, they just want to go ahead and get a kidney from their relative, from their family member. So until the law is changed, there's lots of impediments to kidney exchange that remain in Brazil. Okay, now one last set of controversies that I've been dealing with, and that is quite a bit down the road for Brazil. First, we have to get kidney exchange going in Brazil, is how about small countries or countries that don't have a lot of kidney exchange? And even the United States, when you talk about the hardest to match patients, is a little bit too small. There are patients who are so hard to match that we can't find them a match in the American kidney exchange pool. So what's a natural thing to do is cooperate across borders. But for a long time, the World Health Organization and some of the transplant organizations say that countries must be self-sufficient in transplantation. And when economists hear this, we think it's crazy, right? We don't insist that countries be self-sufficient in other kinds of trade, although having some domestic capacity is, often gives you more resilient supply chains. But now there's been a movement to try to remove that objection. So, for instance, in the US, we sometimes invite in, here's a case, we invited in a patient from Mexico, the lady standing next to me in the yellow dress, and she had a previous transplant in Mexico, but needed another, and there isn't really kidney exchange in Mexico on any scale, so she wasn't going to be able to find a match in Mexico, but she could come to the United States, and she got a kidney from in a chain that was initiated by an American woman, and she got a kidney from an American woman who was 67 years old. And at that time, this is in 2011, or I'm sorry, it looks like it's in 2016. I don't see clearly now when it is, but at that time, American surgeons were reluctant to take kidneys from 67-year-olds because they somehow thought of 67 as being old. Now, many of us remember when we were 67 and we weren't old. So indeed, her kidney is working fine in Marisol, and this chain was also extended. So kidney exchange is the kind of thing that almost by definition is non-exploitative, because each pair gives a kidney and each pair gets a kidney. So so there have been other kidney exchanges, like I was in the United Arab Emirates for the first kidney exchange between the United Arab Emirates and Israel in 2021, and some of those have continued on. And as you can imagine, there were other problems than just the medical logistics that had to be solved to get them to cooperate. And that makes me hopeful that one day the US and Canada will be able to cooperate on cross-border kidney exchange, which we so far can't. Canada has fine kidney exchange, but only 30 some odd million people live in Canada. And so they have lots of hard-to-match pairs who they can't match. And in the US, we have hard-to-match pairs that we can't match. But there's obstacles of various sorts to cross-border exchange. Now, one of the reasons the World Health Organization doesn't like cross-border exchange is the same reason they don't like payment for kidneys. They worry that the rich countries would suck organs out of the poor countries. Okay, so there's been a long view that we shouldn't have black markets, and the black markets, some of them are terrible, and that if we allowed payment, then conventional kidney transplantation would start to look like black markets. Now, I think that's a mistake that economists recognize right away. Black markets work very differently than regulated markets. In the United States, we had a period from in the 1920s to early 30s where we tried to prohibit the manufacture and sale of alcoholic beverages. So this was called prohibition. And it didn't work, and we stopped it. And of course, having a legal market in alcohol doesn't solve all the problems of alcohol. There's still alcoholism and drunk driving, but you can no longer buy whiskey from gangsters, right? If you want to buy alcohol now in the US, you go to expensive stores that sell you Scotch whiskey, things like that. So the World Health Organization has opened the door a crack and said that they understand that black markets are caused by kidney shortages, not by kidney payments. You know, the cause is shortages. So we're trying to walk through that crack, and there was, and some of the black markets are terrible because the laws against payment have driven the surgeries outside of hospitals in many cases. So here's a snip from a video from someplace in South Asia where I've obscured the pictures of the surgeons, because when I present this at surgery conferences, there's always the chance that they'd be recognized. But I've left enough of the faces so you can see they're not wearing masks and they're not wearing gowns. This is not a surgery going on in a sterile environment. So black markets are well worth stopping. And I see that I'm almost well worth stopping. So let me just say that at a consensus conference in Cairo, we endorsed the idea of kidney exchange across borders. And one way that could work in a place like Brazil, which is trying to start kidney exchange but doesn't yet have a lot of patient-donor pairs, is you could cooperate, for instance, with a country like Uruguay, which has only 3 million people in it. And so Uruguay is not big enough to find matches for hard-to-match pairs, but given the number of deceased donor transplants that are done in Brazil, a hard-to-match patient from Uruguay could come to Brazil and start a chain when he'd get a deceased donor kidney in Brazil and have his intended donor continue the kidney exchange chain. So there's things to think about. But the next step is to amend the Brazilian law. And I'm hopeful that can happen because a similar effort just succeeded in Germany. Germany has had basically the same kind of law that Brazil has, which says you can only get a kidney from your family member. But earlier this year, in March of this year, they passed a new law that keeps the idea that we want transplants to be within family members, but now says you can do kidney exchange if the patient and their intended donor are in the same family. You can now do an exchange. You know, if you want to give a kidney to your brother, but you can't because you're not compatible. And if I want to give a kidney to my sister, but I can't because we're not compatible, the German law now says, okay, we're confident this isn't an arm's length financial transaction. This is a family transaction. And now it's okay for me to give a kidney to your brother and you to give a kidney to my sister. So I think that's the minimal revision that we need in the Brazilian law, along with non-directed donation. That would really help a lot. And the general plan, this is my last slide, is to return to Brasilia after maybe 20 kidney exchange transplants have been done and say, the clinical trial works. Kidney exchange works in Brazil. We can follow the patients and the donors. None of them were purchases. It's time to change the law. Thank you.
Thank you. That's great. You can all see why I was so enthused about working with this guy. That's really, really important work. I think we could probably have time for 1 or 2 questions before we break. Al, if you want to come back up here. Are there any questions from the audience? Oh, yeah, down there.
So this is probably a question for a mathematician. Paired is strictly not what happens in a 6-way exchange, correct?
Say
when you say paired, it's automatically that chains are allowed because it's not strictly a
the
pair.
chains, except for the non-directed donor who begins the chain, the participants are patient-donor pairs. And then at the very end, you can have a donation to someone who is waiting for a deceased organ donor and doesn't have an intended living donor.
Yeah, okay. So my question was, paired doesn't mean the pair of 2
No.
It could be any, yeah.
Well, so there's been controversy about that too. In India, we're trying to help kidney exchange, and there was a court in New Delhi that said what you just said. It said the new law only allows pairs. I'm sorry, it wasn't a court, it was a regulatory body, but the high court in New Delhi overruled that and said, no, we mean any size exchange can go through in India.
It's paired, thank you.
All right. Thank you all again. Thank you, Al. Time for lunch.
So, if you are invited to lecture, please follow us to the Sweden restaurant because lunch is going to be there today, okay? We'll take you there.
Teste, teste. Ei, ei, tá me ouvindo? Tudo bem?
slides up here?
I don't know. Are any of those?
Nope, it's PowerPoint slides. I have them here if you don't.
Well, please, if you could provide it, because I don't see them here. Oh.
Here's the wireless network.
I'll grab a pen drive.
Take too much of your time. But there's so much, many nice things to say about it. Do you want me to hold a sign? 10 minutes left or something like that? What time do we go from? I'd have to look that up.
Till 1:40.
So I mean, I can do 10. Fair enough. because really you don't want to hear me. So if my words of introduction are premature, more time for Paul. Paul, of course, is known to you. He's known to me. He needs no introduction, but I felt that I should fill the space and try to say something that he hasn't heard exactly before. So I tell the story that 35 years ago, I was on the tenure committee at my university, and a group of 12 of us had to review important personnel cases throughout the campus. And when you do that, you don't spend any time on the bad cases. You just go like this. You don't spend any time on the good cases. You just go like this. And the mediocre cases you talk about. And a couple of people on the committee, a physical oceanographer and a physicist, and I got together and said, well, why don't we talk about the good stuff? And we've met annually, and we ran out of UCSD professors to talk about. And each year now, my friends say, so Joel, tell us about the Nobel Prize winner in economics. And the physicist in particular was a very, very tough judge. And many years I left this conversation feeling depressed that either I couldn't explain the excellent work of my distinguished colleagues or it wasn't good enough for the physicists. But one year I had the opportunity to tell these guys about auctions, and they understood the importance of this kind of markets for transactions. They understood the importance of formalizing this. They almost understood the value of thinking about large numbers and relating general equilibrium and auctions. And at the end of the story, I'd moved to describing Paul and Bob's work on auctions to the sort of growth of the industry of market design and actually bringing these ideas to real institutions. And they said, oh, a deliverable. And at the end of this talk, the physicist looked at me and said, they would be decent physicists. I didn't have a chance to talk about Paul's wonderful work with John Roberts, his work with Holmstrom, ideas on market microstructure, a variety of things that perhaps are enough for 4 or 5 really wonderful careers. But I want to thank Paul for not becoming a physicist so that we can enjoy his work today.
Wow, thank you, Joel. That was beautiful. I appreciate it. Sergio, I have something here for you. What's wrong with the mechanism design picture up here? I'm going to talk to you today about some problems in algorithmic mechanism design. Some of you may know that I have been working in some real applications for which computing the optimum is just very hard, and we don't actually attempt to compute the optimum. We run certain algorithms that perform pretty well. And there's been a bunch of work going on by computer scientists in that area too. And the algorithmic mechanism design is about finding good algorithms and then pricing schemes that go with them so that, for example, truthful reporting of your values to the algorithm is a dominant strategy, for example. And then a few years ago, together with several of my friends and co-authors, we began wondering, well, suppose we actually succeeded in having a lot of these kinds of markets existing in the world. Would this resemble in any way what we know from general equilibrium theory? Would it be true that just because we were doing a pretty good job of allocating goods in each market, that, for example, the investment incentives were right in the market, that somebody would invest would invest to improve their value exactly when it increased the social surplus. And that's a paper that I did with Scott Commoners, Mohammed Akbarpour, Shengwu Li, and Kevin Li were 5 authors. Lots of we published that in Econometrica a few years ago. So that became algorithmic mechanism design with investments. And I'll tell you a little bit about that because I imagine most of you don't know about that, and you'll probably need background. A lot of this talk is going to be background in all these areas because I think big parts of the audience won't know one piece or another. And then I began to wonder, well, suppose we come to something like the limit case. And FPTOS, which I'll define for you formally in a little while, are algorithms or algorithmic schemes that are very good so that we come very close to the optimum and ask, if we got very close to the optimum, would the investment incentives be very close to the optimum? It's going to turn out that the answer is sometimes yes and sometimes no, and I'll highlight for you exactly how that works, trying to understand that if we ran markets this way and then didn't just do partial equilibrium, how would the whole system work? So that's what the subject is about. So here again, here's a competitive equilibrium with investments. If you do general equilibrium theory and if all the markets clear, then among the markets that clear in general equilibrium are the investment markets. And we have our first welfare theorem. It must be that people have the incentives to make the right investments. Now, we also know, or some of us know, and hopefully more of you will know now, that if you run a VCG mechanism, any of the VCG mechanisms, and you have, and Joel, you're a participant in this VCG mechanism, and you know it's a dominant strategy to report your values truthfully, that if in that context you have the opportunity to make an investment to improve your value, it'll be in your interest to make that investment if and only if it increases social surplus on net. That's a theorem of Rogerson's from 26 years ago, or 36 years ago. Holy cow, 36 years ago. So it's been known for a long time. See, I can do subtraction. Okay, so what I want to know is algorithmic mechanism design identifies algorithms that produce nearly optimal allocations, and it has prices, the version we're looking at anyway, has prices that will make it in your interest to report truthfully. And so the original work on this algorithmic mechanism design with investments I published with the co-authors I mentioned in Econometrica. So what about investments for fully polynomial time approximation schemes? And most of you won't know what that is, so I will explain it to you. The background I will explain before we go into my results with these three pieces. What do I mean? What are approximations? What's that all about? What are fully polynomial time approximation schemes? What's algorithmic mechanism design? So I've got a few slides on this to make sure that you all have the background you need to see what we have done. Okay, so about approximations, there are a lot of problems out there that computer scientists and operation researchers know that are really hard to solve numerically. Basically, convex optimizations are relatively easy. You take, wherever you are, you start with something feasible, you take steps in improving directions, eventually you can get up to an optimum. Many of those algorithms are pretty fast. But when exact optimization is not possible, well, there's a huge literature out there. Here are three of the books that have been written: combinatorial optimization, approximation algorithms, the design of approximation algorithms. And there are theorems in these books. And the theorems say things like, here's an algorithm I can run that guarantees to get me 52% of the optimum, or here's and they tell you the quality of the approximation. And the second thing they tell you is computation time. They say, if it takes n bits of data, I can run this thing in n cubed steps or less. Some measure of how long the approximation is. So the theorems are about quality of the approximation and computation time. Okay, so what's an FPTOS? A fully polynomial time approximation scheme is a family of algorithms parameterized by epsilon, such that for every epsilon greater than 0, the algorithm will generate a feasible solution with a value that's very close to the maximum, at least 1 minus epsilon times the maximum. And it'll do so in an amount of time that's a polynomial function of how much data there is and 1 over epsilon. So for example, I've given you 2 examples of possible theorems about computation times. The first, you might have a sequence of algorithms that you can prove will run in an amount of time that's on the order of n cubed times 2 to the power 1 over epsilon. That's called a polynomial time approximation scheme because it's a polynomial function of n. But it's not a polynomial function of epsilon. As a function of 1 over epsilon, it's exponential. If you're trying to make your algorithm really good, you're going to pay a high price for improvements in the algorithm. A fully polynomial time approximation scheme is something that has a runtime like, for example, n cubed times epsilon to the minus 2. That's something that's a polynomial as a function of n and also as a function of 1 over epsilon. Okay, so if you have a fully polynomial time approximation scheme, you've got a set of algorithms that for not too high a price will let you set epsilon pretty low and still run pretty fast. Okay, so these are in some sense the easiest approximation problems in the NP-hard class. Okay, now there are a bunch of problems that have fully polynomial time approximation schemes. Here's a list of some of them. The one I'm going to talk about most is the first one in this, the knapsack problem. For those of you who don't know the knapsack problem is that I have a bunch of items, they have values and they have weights, and I have the ability to carry 50 kilos. That's some weight limit that my knapsack has, and I want to put the most valuable items into the knapsack subject to not exceeding the weight limit. That's an NP-hard problem because if the items are not divisible, then figuring out which combination of items to put in can take a long time. But there is an FPTOS for that problem, which I'll show you later. There's a way of doing this approximately that gives you a 1 minus epsilon approximation of the optimum in a time that's a polynomial function of the, actually it's even works with pseudo-polynomial, I won't even get into that, but polynomial function of the number of bits it takes to describe the problem and 1 over epsilon. And there's several other problems that also have FPTOS. Okay, and the last bit of background, or almost the last bit of background, is given us a class of problems parameterized by values and constraints, along with an approximation algorithm, its associated outcome function, so and a payment rule. So this in this particular example that's written here, there are k possible outcomes for each individual, and the individual has values for each of the k possible outcomes. Outcome 0 he has value 0 for, and there's a payment rule, and the agent gets a payoff that is his value. This is agent n's value of the outcome when his payment is Pn, and the payment depends, the outcome depends on value reports, the payments depend on value reports. This is mostly familiar stuff to all of you. Notice that whatever the algorithm is, there's going to be some outcome function x and some payment function p, and that's the mechanism. We usually talk about mechanisms in terms of outcome functions, not in terms of algorithms. The incentives depend only on the outcome from the individual's point of view. And the mechanism is said to be truthful if for all value profiles, truthful value reporting is a Nash equilibrium of the game. That's almost the same thing as saying that it's a dominant strategy to report truthfully. Okay, now I am going to limit attention here for simplicity to packing problems. This whole theory generalizes, but we're going to limit attention to packing problems. I'm doing that largely because the cases that I've actually had to implement in real life have been packing problems. When I was working on revising the allocation of radio spectrum in the United States, and we were talking about buying the broadcast rights from some television broadcasters as part of the problem. The question was we needed to pack into the radio spectrum into a set of channels which broadcasters were going to broadcast. That's a 0-1 question. There, you either include them on the spectrum or you don't, and that was represented as a packing problem in our analyses. And there are a lot of applications like that. You're deciding, which airplanes get to land on a runway, or you're well, you can think of lots of examples of packing problems. So formally, what's a packing problem? For each individual n, there's some value Vn of being packed. I want to have space for my airplane on the runway, or I want my television station I want to have a channel to broadcast on. I get a value 0, that's a normalization if not packed. And there is some subset of 0, 1 to the end, which are the feasible packings. The goal is to maximize welfare, as it's called by the people who do this. So given the outcome function x, wx, when the value profile is v, is just the sum of vn xn. So remember, x is 0, 1, so I count vn if xn is 1, and I don't count it if xn is 0, and that's the total value that I get from my packing. And I'm trying to maximize that subject to lying in the capital omega. Okay, again, a little bit more about the incentives. A packing algorithm is said to be monotonic if for item n there exists a threshold function, tau n of v minus n, and is packed if its value is high enough. So if Vn is bigger than tau n of v minus n, so if I'm trying to get my plane onto the runway and I say a landing slot is worth $10,000, if my announced value is high enough, I'll get packed, and how high it has to be depends on everybody else's announcement. And it's not packed if I put less than that. So if my threshold is $8,000, that means if I quote any number larger than 8,000, I'll be packed. And if I quote any number less than 8,000, I won't be packed. And the threshold payment rule is a payment rule that says that PT, the superscript T there means threshold. The payment rule is that when I'm packed, I pay my threshold value, and when I'm not packed, I pay 0. And the reason that's interesting is that a direct mechanism in which people report their values, the direct mechanism XP is truthful if and only if these two things hold. The algorithm X is monotonic, and there exist functions Fn such that the payment rule is the threshold rule plus any function of the other people's values. This looks, for those of you who've seen the theory of the Vickrey-Clark-Grove mechanisms, it looks very much like that, and in fact the proof is very much like that. If you add a function that depends on everybody else's values, you don't change the incentives for individual n. And just as the pivot mechanism is unique for the Vickrey auction, that is, this threshold mechanism is unique for this auction, and this is the complete set of payment rules that make this mechanism truthful. And that's important to us because it leads to some immediate Okay, it will lead to something in a moment that's pretty immediate. I'm just going to anticipate it here as I talk to you. The incentives that you have to invest don't depend on the payment rule. Once I have X, there's a threshold rule and there's these other rules, but the Fn of V hat minus N doesn't depend on whether I invest, doesn't depend on what I report, and consequently my investment incentives don't depend on which truthful payment rule is used. I can speak of investment incentives as being a result of X alone, and that's going to be important for me in a little while. Okay, now I'm going to show you a silly example that is, the referees didn't like the first time we submitted the paper, but it has everything important in it, even though it's silly. So bear with me as I go over a silly example. This is going to be a packing algorithm with a 99% allocation guarantee. And what is this algorithm? It's a satisficing algorithm, as we call it. If the most valuable item is at least 99% of the total value, pack it alone and stop. Otherwise, maximize exactly. Okay? You can't get less than 99% of the value doing this. It's an example of an algorithm that guarantees you 99% of the value. So the value of what you pack divided by the optimal value is at least 99%. Pretty silly algorithm. Nobody would want to do this. But what's interesting about it is that it has a 0% investment guarantee. Okay, so this is a really bad algorithm when we consider investments. And why is that? Well, here's an example. I've got 3 bidders. Each has a single item to pack. Bidder 1's value is 0. Each of the other bidders have a value of 1. And it's feasible to pack all 3 items. Very simple. We're going to use a threshold mechanism. We're going to set prices to be the threshold prices. And the threshold prices are all 0, because no matter what, since it's feasible to pack everybody, as long as you have a positive value, it's feasible to pack you, we're going to pack you. Okay, so let's think about bidder 1's investment incentives. So bidder 1's always packed, its threshold price is 0. And assume that by investing at a cost of 200, bidder 1 can raise its value to 200 plus epsilon. Well, it's going to be packed. That's worth something to it. It's going to make epsilon more. So bidder 1 will invest, and it'll be packed. But now its value of 200 is more than 99% of the total value. So it's going to be packed alone, and bidders 2 and 3 are not going to be packed. So the net value of the packing is going to be 200 plus epsilon. That's the value to the bidder, minus its cost of 200. That's epsilon. And the optimal value in the investment problem is 2. I could, if he didn't invest, we could have had a value of 2. So the value of this problem is epsilon over 2. That's not the minimum. If you take the infimum of this over epsilon, you get 0. This is an algorithm that guarantees you 99% of the value in the allocation problem, and it guarantees you only 0% of the value in the problem with investment. All right. Now I'm going to do a lot of abstract mathematics with this in a moment, but this is exactly the only thing that this is something that can go wrong in real algorithms, and it's the only thing that goes wrong that prevents value. So I'm going to dwell on this example for a few moments. What happens here is that bidder 1, by making an investment, bidder 1 was going to be packed anyway. And by making an investment, he's still packed. His value goes up. That's monotonicity guarantees that. But he has a huge negative externality. There's very little gained. He gains epsilon net through his investment, but he causes a massive negative externality. So we're going to call that later in this talk a confirming negative externality, where, is that a question? You don't understand in which sense it's... in which sense it's... Don't worry about it being an auction yet. Or I'll answer your question anyway, but this is not just about auctions. But if each of these guys names in general for packing problems, everybody names a value. And if the amount you name is high enough, you get packed, you're a winner. And you pay a price which is determined by this formula. In this case, the formula gives a price of 0. It's what a second price auction would do. If I had 3 items for sale and 3 bidders, a second price auction would pack the 3 highest valued guys and charge them each 0. That is it's an auction in that sense. But it's not really important to me. What's important to me is that it's a mechanism that's a truthful mechanism, and it leads to a minimum investment value of 0. And getting back to the real theme of this example is that what happens in this example and what happens in real algorithms, as I'm going to show you, is that there can be huge negative externalities that are caused when somebody who was going to be packed anyway increases his report, doesn't affect his own value at all, but drastically reduces the value to other participants. And I'll show you that, and that can go wrong, and it screws up efficient investment. And there'll be a theorem later that says that's the only thing that screws up efficient investment. If that doesn't happen in the algorithm, then the algorithm is going to perform really well in the underinvestments. So this silly example, nobody would ever use an algorithm like this, but it captures what's important that's going to go on in the mathematics, okay? All right, so some key generalizable observations. An algorithm can have good allocation performance by being clever about high-value choices while still being careless about other choices, as this algorithm, the satisficing algorithm was. With investments, high-value choices that look like they're high value, the 200 in this example, may actually be adding very little net value. In this case, it was adding gross value of 200, but net value of only epsilon. And the investment performance is really being determined by other choices that the algorithm makes. And investment performance for approximation algorithms can be ruined by negative investment externalities. Now, one of the things I'm going to want to say to you in a few moments is that negative externalities is a phrase that's come to be confused. I often hear economists and game theorists talking about externalities in a way that's different than the traditional definition in economics. I'm going to define externalities in a moment, and I will repeat that again because it may not, some of you may be used to a non-standard definition different from the original definition of the term. Okay, so externalities and investment incentives. Okay, so the first theorem is one I've already described to you, that if you have 2 truthful mechanisms with the same allocation function x, if xp and xp hat are both truthful, then they have the same investment incentives. N's net return to changing his value from Vn to V prime at any cost C is the same for both mechanisms. That's because these payment rules differ only by this thing that's not affected by the investments. Externalities, suppose XP is a truthful mechanism. Given the mechanism, when player N changes her report from Vn to Vn tilde, her externality is defined by this expression. And the expression is the sum of the change in others' values minus any extra payment she receives. So it's traditional in economics ever since, you know, as long as for the 100 years that externalities have been discussed, it means that I'm using some resources in a way that I'm not paying for. Now, it's sometimes in game theorists or mechanism designers sometimes talk about Vickrey Clark Groves and say, oh, I'm making a decision and it's reducing the value of others, and that's the externality. But that's not the traditional economic notion of externality, because if I pay for what I'm taking something away from Pradeep. If I pay for what I'm taking away from Pradeep, then it's not an externality in the traditional economic terms. And so our definition of what an externality is, of changing from V to V hat tilde, includes or subtracts off any extra payment that the individual might make. Okay, and now if there are no externalities, if this externality is always zero, then N profits from an investment if and only if the investment increases net welfare. In fact, you can prove that if the externalities are all zero, that the allocation maximizes objectives subject to some constraints, not necessarily the real constraints, but some constraints. That's one of the theorems in my original paper. The main findings of this whole line of research are going to be, first of all, the one you've seen, all truthful mechanisms with the same outcome function have the same investment incentives. So I can associate incentives with algorithms or outcome functions. I don't have to talk separately about which payment rule I'm using. Every non-optimizing algorithm necessarily entails non-zero externalities. There are going to be externalities if it's not an optimizing algorithm. And that can sometimes incentivize welfare-reducing investments. An FBTOS can consist of entirely of algorithms that guarantee a zero fraction of possible welfare when an agent invests optimally. So that example I showed you, I'm going to show you again in a more complicated example in an FBTOS, where exactly the same thing happens, even though it's a fully polynomial time approximation scheme. There can still be investments that result in the net value of when I follow this thing of zero, and I'll show you that that's possible. An algorithm that excludes confirming negative externalities has the same investment guarantee as its allocative guarantee. So if I don't have exactly the problem I showed you, where I can make an investment that doesn't change my allocation, where I've increased my value of an allocation and caused a negative externality to others, if that's not present, then the algorithm has the property that if it was a 75% approximation without investments, it's still a 75% approximation with investments. This is what I showed you is the only thing that can go wrong with investments. And then what's newest, most of this is all in some version in our first paper. What's newest that I just proved a few weeks ago is that every FPTOS can be converted into a monotone X-cone FPTOS that is given any fully polynomial time approximation scheme. I can find another fully polynomial time approximation scheme that doesn't have the investment problem that's described, that I've been describing. So we can, if we have good approximation schemes available, we can modify them, good enough approximation schemes available, we can modify them so that there is no investment problem associated with them, and that's sort of the main new finding. Okay, let's see, it's almost 1:30, goodness. All right, worst case analysis. This is the satisficing algorithm, which I'm reminding you of. The question is this example general in some sense? And I've already indicated to you that the answer is there's a sense in which it is exactly what happened, the problem that an investment can transform low-value items into high-value items without affecting net welfare, and that can screw up a satisficing type algorithm. Okay, even an FBTOS can have that problem. So I'm going to actually just leap into, given the time, a particular FBTOS. This is one for the knapsack problem that I've described to you. It's a famous one because they took an FP-TOS that wasn't monotonic and converted it into one that is monotonic so that it could be used, so that you could have truthful incentives with it. I'm going to further transform it into one that's monotonic and X-cone so that it also has good investment incentives. And this will serve as an example. What I'm going to do to this one, I can do to any FP-TOS, and it'll give you an idea of how the whole thing works, and I'll try to finish on time with that in mind. So here's how it works. Given n items and given a value profile for those n items, and given an epsilon greater than 0, the way this FP-TOS worked is it creates a series of knapsack problems. Now, I want to just give you a hint as to what's going on here before I get going. The way the fully polynomial time approximation scheme works is it approximates the problem, then solves it exactly, the approximate problem, and then uses that as a approximate solution of the original problem. So the approximations we're looking at here are taking a look at an original problem that we're given, writing down a series of other problems that are close, solving those problems exactly and using them to find as our approximate solution. And here's how it works. We have a bunch of values and we're going to create a step size gamma, which if you take L equals 0 here, step size gamma is just epsilon over n. And we're going to take larger step sizes as we move along. And what we're going to do is for the Lth problem in this sequence is we're going to truncate we're going to replace the values. We're going to turn these into steps. So we're going to ask Vn divided by gamma L. How many steps is that? This notation is supposed to mean the integer, the next integer lower than that. So I'm going to take something and say that's 20 steps. And I'm also going to put an upper bound on it, which also depends on L. Okay? So for larger L's, I'm going to have larger step sizes, but also a larger bound. And then what I do is, after I've done the rounding, anything that has a value of 0, I'm just going to toss out. And then I'm going to maximize, if there's anything that has a positive value, so there's some problem left to solve, I'm going to solve it. And as L grows, eventually, at some point, everything has value 0, and that I'm done. So this is a series of problems that looks a lot like the original problem. It just rounds down, truncates the largest value, and it turns out there's a dynamic programming solution you can use for these problems, that the size of the dynamic programming table has to do with, first of all, what's the largest value you can get, and how many step sizes there are along the way. And this is going to make the number of steps being proportional to 1 over epsilon. So when epsilon gets small, I have more and more steps, but this dynamic programming algorithm is going to be polynomial time in the number of steps that I have to consider, and these will be all able to be solved quickly. And then what these guys did is they chose the allocation that among all these problems that are solved, it picked the one that it picked the one that gave you the highest value. Okay. And it's a theorem then that for every epsilon greater than 0, this scheme is monotonic. It guarantees a 1 minus epsilon of the maximum, and it runs in time that's fully polynomial. Okay, that's how the algorithm worked. Now, unfortunately, this algorithm has a 0 investment guarantee because it's taking all these small values and rounding them all to 0, and that can be very painful if somebody makes a big investment that doesn't really add any value. So for all delta greater than 0, there's an epsilon less than delta. such that this rule with parameter epsilon has an investment guarantee of 0. Okay, that's the, and it's done exactly the same way as the silly problem. Somebody makes a very big, somebody who was going to be packed anyway, makes a very big investment, drives all the other values to 0. Those items don't get packed, and we get a bad outcome. Okay, now the externalities that I need to block, if we raise the value of an already packed bidder or lower the value of an already unpacked bidder, the total value of the other bidders does not fall. That's what I'm going to, well, if it does fall, that's called a confirming negative externality. It's confirming because I was going to be packed anyway. It's a threshold mechanism. When I increase my value, I'm still going to be packed. And if doing that can cause damage to others, that's a confirming negative externality. And similarly, lowering the value of an unpacked bidder. Okay, and so here's the formal definition that says the same thing in mathematics. And the theorem is that for any beta, if X is X cone and a beta approximation, then it's also a beta approximation with investment. If there are no confirming negative externalities, you don't lose anything at all in the investment problem. Okay, and let's see. I have 5 minutes, so I'm going to show you how to turn that particular FPTAS into one that has no confirming negative externalities. And it's very small, subtle change. We're going to fix this by picking L star, which of these solutions we look at more cleverly. And the original algorithm chose L star as being the one that gave the highest value of the approximating problem. And the new one says, you know, okay, I've got a bunch of possible solutions, one for each L. I'm going to use the actual values, Vn, rather than the approximating values, Vn epsilon L, to choose my solution. So that if some of the approximate solutions I'm generating, you know, throw out lots of things with small values, well, that's going to be accounted for when I pick L star with the blue choice, where it wasn't being accounted for with the red choice. And I'm pretty much out of time. I'm almost out of time, so I will tell you that this technique solves the problem, and this technique similar to this solves the problem for every FPTAS. That what you need to do is make sure that you pick the right approximating problem to generate your solution. And the way the proof of that's going to go, I think I have enough time to do this actually, is that this is something that will be familiar to many of you who've worked on mechanism theory. A mechanism is bossy if for any value profiles, if you make a change from your reported value from you know, Vn to Vn prime, and if that changes the, if you make a change that doesn't affect your part of the allocation, so Xn is the same, but it does affect other parts of the allocation, a mechanism with that property is called bossy, and a mechanism that doesn't have that property is called non-bossy. If you have a non-bossy mechanism, it can't have any confirming externalities. So with non-bossiness, I wouldn't have the problem, but I have one little twist on that. Optimization algorithms, like I'm running at all of those L's, are non-bossy and therefore X-cone, and an algorithm that outputs the highest value allocation from among multiple X-cone algorithms is X-cone, unless you vary your tie-breaking rule among them, which is a detail I will leave out for the moment. So what was going on in the BKV algorithm, where it's running a bunch of optimization algorithms, they're all non-bossy and therefore X-cone, and where I take the one that chooses the highest value, I have I have something that's still X-cone, and therefore, I have fixed my algorithm so that it does have the desired investment property in addition to being a fast algorithm and in addition to having truthful reporting incentives. And I guess that's the XCone version. There's the main findings again. And I see Joel standing out here telling me it's time to take questions. So, Joel, do you want to? Time to take questions. There we go. Which slide?
The previous one.
This one?
Yeah, thank you. That's all.
Taking it back to another question.
There, on the right.
So many thanks for the talk. If we talk about packing, so what could be like the economic applications of that? So you already mentioned auctions, but kind of what else can it mean? Someone being packed and someone being not packed.
Well, what other economic things? I think in the economic context where it's decentralized, where you can be packed or non-packed, where that we're talking about, I either sell to you or I don't, and all of those things can be done as auctions. I had the question, in what sense is this an auction? Well, let's just agree we're going to call all of those things auctions, and that's the application of this. The whole FPTAS thing could be done in general for machine scheduling problems and so on. And if you regard every allocation problem in which an allocation is done or not done and you make a payment, if you regard them all as auctions, then I discovered last year when I was testifying in the Google antitrust, one of the Google antitrust cases, that the court didn't have a clear idea of what the word auction meant, and I came to realize neither do most economists. So I don't know what you would include under the term auctions, but to me these are all auctions.
Thank you one more time.
Okay, now we have a coffee break. And just a reminder, there will be a bus at 6 p.m. that will depart from here to the dinner, okay? Thank you.
And the dinner is at the venue isn't in the program. You might want to say, in case anybody is coming from their home, where they're supposed to show up.
Okay. The dinner is going to be in Sala São Paulo, okay? In English, it's like Room São Paulo in the center of the city. 6 horas. Isso. Yeah.
Cada atendente da sua equipe usa um número diferente no WhatsApp? Além de não ser profissional, você fica sem visibilidade.
That's strange. That's I can hear there. No one called it out. Robin, that's
Muitos refugiados estão passando fome. É por isso que a gente veio te fazer um convite.
That's strange. That's I can hear there. No one called it out. Robin Answer saying a Federer said no, it's definitely out.
Are you allowed to do that?
Well, that's why he wins the sportsman every time.
Now. So there's small answers. One is that my motivating question is a straw man. People actually always lie when it's in their material advantage. Another answer, which is easy, is that material advantage isn't everything that motivates people. A third answer is that it's the folk theorem. That is to say, all of our interactions are embedded in long-run relationships, and what passes for myopic optimization may not in fact be optimal in the long run. And the other is, without defining it now and perhaps not ever, somehow norms or societal expectations matter. And my response to this is that these small answers have an element of truth, but the first small answer surely doesn't apply uniformly. That is to say, we know some folks who are honest. And the second thing is that norms perhaps is almost like repeated games, too big of a category. So what I want to try to do now is sharpen the small answers. And I'm going to do this by looking at a particular category of environments and try to organize sort of observations and then add a little bit of theory. And my playground, as it will be, is going to be high stakes sports. So the kind of competitive games that we watch. And you probably would think that somebody who has a perfectly good career studying equilibrium refinements and communication games would only do something like this if in the background he was a fanatic football fan or loved tennis or something like that. And the answer is no. You all know more about these sports than I do. I'm going to tell you some anecdotes. I practiced some Portuguese, e como falar uma língua nova. So for me, it is like me trying to speak a new language when I talk about these games. You are going to listen to my anecdotes and know that they are wrong. So I want you to sort of suspend disbelief or give me a little bit of flexibility, and then if you wish to beat me up in the questions or at dinner tonight. So I think that starting with Steve Levitt, who studied sumo wrestling in Freakonomics, it's essential for people who are going to talk about baseball to say, well, we understand that more things are important, but we may still learn something. So in some sense, a sentence to motivate the exercise I'm trying to think about is from Aristotle, who asks or says that sometimes good laws make good citizens. Those of us who are comfortable with mechanism design understand that a lot of what we do or we can do is build a game and see how people play. And I'm going to be thinking not so much of the process of building the games, but of thinking about how the games that have already been built influence how the actors inside of them behave. And again, we can think about this tension between, I don't know, maximizing monetary utility and what people actually do, and some examples that perhaps aren't as frivolous. So there's tax compliance, that is to say, following the law and maybe even the spirit of the law and paying your taxes. There's tax avoidance, where you follow the law literally, but you make sure that you minimize your contribution. And there's tax cheating, where basically you're homo economist and you look at the rules and you'll be willing to break those rules if it's to your monetary value. And I would argue that at least in some places, there's a lot more tax compliance than a standard model of maximizing behavior would predict. And I would even argue that I like to live in that world. Obeying speed limit, there's signs where I live that say speed limit 55 miles an hour. And if you were to follow those signs in times when there's no traffic, you would put yourself in danger because all of the other cars are moving much faster. So there's a law, and we violate the law in sort of, in a sense, in a rational way. Traffic lights and gardens. I tell the story of living in Wassenaar, Netherlands, about 12 years ago on a sabbatical. This is a small, affluent town. I had an apartment. At the street corner, there was a traffic light that had 3 different settings, one for automobiles, one for pedestrians, one for bicycles, all going in the same direction. So if you were to follow these rules, you would stand in the corner as a pedestrian, watch as all the cars were going by. There would be no traffic to interfere with you. Watch as all the bicycles go by. There'd be no traffic to interfere with you. And then it would be your turn. And I come from a culture where doing that, following the rules, would be a complete waste of time. So the first time I entered this corner, I walked when it was free, and there was a small Dutch woman with a loud voice who started speaking to me in Dutch. And I turned to her and said, Engels? And so she started speaking to me in English, and she basically said, you barbarian. So I was disciplined, and for the rest of the year in Wassenaar, I stood at the street corner, and I want you to know that I met that woman one more time, and I was at recycling bins, and I was carefully putting my white bottles into the white bin, the brown bottles into the brown bin, and she came up to me and she thanked me. Gardens, the story that I sort of view as a puzzle is, would you prefer to live in a world where the beautiful gardens are not trod upon because everybody's mother and father taught them that you don't trod upon gardens, or in a world in which there are very cheap, inobtrusive, but powerful guards standing at the corner of the gardens, protecting the gardens and there to enforce the law? And I think that I prefer the first world, and I'm not sure I understand why. So I'm trying to figure out things like that. So I'm almost ready to start with my anecdotes. I should warn you that the talk is anecdotes, sort of outrageous claims, and then 3 little theoretical models. So if you never bluff in poker, that doesn't make you a good person. It makes you a bad poker player. So even if your mother taught you to be moral and never lie, the rules of the game remove that restriction. On the other hand, if you deal from the bottom of the deck or pull aces from your sleeves, you aren't a good poker player, but you may be dead. And that is to say, there are rules, and the rules are enforced. Now, some people do deal from the bottom of the deck, but they're presumably doing that based on a computation. Okay, so I'm going to give you some examples of high-stakes sports. I'm going to give you audacious organizing principles. Audacious in this case is not a boast. I'm going to make claims in order to sort of fit square pegs into round holes. And then I'm going to give you, if time and my energy permits, a few models. My goal here is to add a little bit of structure. So the world is complicated. I announce in principle that some folks tell the truth for reasons that aren't utterly standard, and I want to have a better understanding of what makes that happen. And I'm not going to give you an ideal gas law. I can't describe anything, but maybe a little bit of structure here. So here's the first thing. I have a video of this, but let's wait. So Roger Federer is a famous tennis player. And 10 years ago, 20 years ago, perhaps he was the best active tennis player. And he was playing in a match in 2018, and he serves, and the line judge gives the point to Federer. And Federer stops the play and says, "It's your point." So Roger Federer conceded a point. There was a stop in the action. He didn't have to do this. He sacrificed a point. It turned out he didn't sacrifice the game, the set, the match, or his ranking. And by virtue of this, he was honored on the internet. So there's a sense that he became a good sport. Now, in this particular case, it wasn't costly for him to do this, but it could have been costly. If you think about what's going on, I think that the natural, the salient explanation is that Federer had a notion of fairness and he wanted to win the game by winning the points. On the other hand, you can easily think of alternatives. He might have just wanted to drive his opponent crazy. He might think that having his picture on the internet conceding a point would allow him to sell more wristwatches. And even if Federer is this moral person, I found a video of Federer. I'm not sure that I could find a video of Nadal or Djokovic or Serena Williams doing the same thing. So it's just an anecdote. Here's a contrary anecdote. Baseball is a game played further north. It's a bat and ball game. Derek Jeter is not quite Roger Federer. If Roger Federer is Paul Milgrom, then Derek Jeter is an MIT professor who has not yet won a Nobel Prize. He was playing baseball, and the ball ricocheted off after it was being pitched. So the batter stands like this, and the ball went off like this. And the action is stopped. And at this point, there's two possibilities. One possibility is that the ball hit the bat and went out of play. That's a little bit bad for the batter. The other possibility is the ball hit the batter, and in that case, the batter is awarded a base, and that's good for the batter. So what happened was that Derek Jeter went, and the umpire awarded him first base. And then I do have the video, but Derek Jeter clearly wasn't hit. And after the game, he said, "This is just part of the game." Okay, so the rules of the game don't prevent Derek Jeter from acting, but he plainly gamed the rules the way that a tax avoider might game the rules to his advantage. So I would say that Derek Jeter is not a good sport in this situation. He absolutely knew what he was doing. After the fact, the New York media, where Derek Jeter played, thought that this was a sign of skill, and the Tampa thought that it was a sign of immorality. When I agreed to give this talk, I thought that there would be a pretty big chance that Brazil would be celebrating the outcome of an international competition at this time. I'm sorry for the country, but perhaps the most famous example of gamesmanship happened 40 years ago when a famous Argentine football player happened to be standing in front of a goal, and the kickball had a miraculous change of direction, scored a goal, and helped Argentina win a World Cup against the unfortunate English team. And after the game, that Maradona was questioned, and he said, "La mano de Dios." So it was God's hand that scored the goal. I believe that if Maradona admitted that it was a handball, something terrible would have happened to his family. So this is a situation in which you have a game in which the culture perhaps encourages people to exploit the rules. So Maradona violated a rule, knew he violated the rule, and didn't take the advantage of confessing. One or two more examples, if you wish. The theory isn't that interesting. The examples are better. So this is a high school students, 15-year-old girls playing basketball in the middle of the United States. And what happened was that the team won a championship on the final shot. They won by a point. And then other things happened. So the coach of the team reviewed the game's video, and he realized that the team they were playing was actually cheated. And midway through the game, a 2-point shot wasn't recorded. And this person could have said nothing. The game and the championship was officially recorded. But instead, he talked to his team, and the next day they forfeited the game and the championship. They didn't offer to replay the game. They didn't offer to replay the game from the halftime. They just said, we were awarded this victory by mistake. So this became big enough news for me to discover it. Lots of positive publicity for coaches and players. I think this is my last story. So cricket is basically baseball for the rest of the world. It's a bat and ball game. And it's a game that, unlike baseball, has a code of conduct. So when you say that's not cricket, you're supposed to be invoking the notion that cricket players enforce their own rules. And this is a counterexample. Australia and New Zealand were playing each other. It was a very tense game, and I don't quite understand the scoring, but New Zealand was down to its last chance. And it was possible for that last chance to do something that, in my terminology, would be hit a home run. But if you hit the ball as far as you can, you get 6, and that would have tied it. And the Australian bowler had the opportunity within the rules of the game to make a pitch that was impossible to turn into a home run. So he rolled the ball on the ground, and the New Zealand player put down his mallet in disgust and walked off the field. And this is a situation where the rule breaking, like Maradona, like Jeter, was not violating any law. In some sense, it was violating cricket. And what happened was the following. The Australians were viewed as really bad sports, a lot of bad publicity. And ultimately, the manager of the Australian team, who was the brother of the bowler, came out and said, this is the worst thing I've ever done in my life. And the laws of cricket were changed to prevent this kind of thing happening again. Where am I going? Who knows? Cricket and baseball examples exhibited gamesmanship. The soccer really literally broke the rules. Handballs are bad. And tennis and the high school basketball were good sports. Is there anything that I can say that would help me predict this kind of organization? Yes and no. So this is an intermediate classification. One thing that I think is important that I didn't think about before starting this investigation was the following. Think about some of these examples. In cricket, the event was rolling the ball, and there was an opportunity to sort of stop the action and consider what's happening without breaking the flow. In baseball, the ball ricocheted off and everything was stopped. And there was an opportunity to reflect on that and to make a decision. In high school basketball, you reviewed the video after the game was over. In United States football, but also typically in international football, in professional basketball, most of the action requires continued movement. So if I foul somebody in football and the referee doesn't stop the game, I don't have an opportunity to say, I made a mistake. So I want to distinguish games that are fast, if you will, and games that you're slow. If you're slow, I say that there's a salient opportunity for good sportsmanship to be present. Okay, this is my audacious summary. So this is an attempt to draw order out of chaos. There are a bunch of different sports, and the first column is labeled team. That one I think is not ambiguous. So cricket is a team sport, baseball is a team sport, golf is typically not a team sport. So the Y is team and N is no. What is stop? Stop means what I tried to illustrate in the previous slide, whether an event leads to a stop in the action. So in my cricket anecdote, it does. In my baseball anecdote, it does. In my basketball anecdote, it does. There are stars there because in baseball and cricket, there are lots of situations where the action continues. So whether you've caught a ball properly is a sort of continuous action. In soccer, typically no. There's an asterisk there because there are situations of what I call good sportsmanship in soccer where referee makes a bad call, awards a penalty kick, and the team awarded the penalty kick, knowing that they don't deserve it, doesn't take the kick seriously. So that's a situation where there's a stop in the action and an ability for the player to behave morally. Golf, the infractions are sort of like stepping on the ball or moving the ball, and you have a chance to say, oh, I stepped on the ball. Tennis, what Federer did. I think the boxing, the boxing and the track, the infractions sort of happen and you can't stop yourself. So there's a little bit of arbitrariness in the second column. The third column is there an honor code? That is to say, if you look at the writings or the impressions of what makes this game work, can you find documentations that say that it's your job to enforce the rules? And in cricket, there certainly is. In baseball, at least as played in the United States, there certainly isn't. I think high school basketball, but not professional basketball, football or and so on, and golf, tennis are examples of situations where you can certainly point to an honor code. Referee is, if you look at the column, I've got a yes everywhere. So in high stakes sports, I couldn't think of an example where all of the action is done without the assistance of a third party enforcer. But it is certainly the case that the degree to which the referee controls things changes. So the idea is to look at these columns and say, is something going on? And I would say maybe a little bit. So stopping and having a norm are in my table incompatible. So it's this column and this column. Okay, there's a weak relationship, I would claim, between norms and referees. That isn't so apparent in the table because I had yes next to all the referees. In order to make it more apparent, I would have to make a judgment about how powerful or how informed the referees were. No norms for individual sports except. So this is a stretch, but I would argue that if you wanted to look for people who behave like good sports, you should look first to tennis and golf rather than to soccer and baseball. Okay. On the other hand, Bobby Jones, who was a golfer from close to 100 years ago, sacrificed a national championship by admitting an error, and he said, "You might as well praise me for not robbing a bank." So he thought that of course you had to play by the rules. There is a German football player named Klose, who he had scored more World Cup goals than anyone until he was overtaken this time. And he has been associated with good sportsmanship on several occasions, and you can find a quote just like that saying, you know, I'm not doing anything special, I'm doing what you have to do. Okay, so what's my enterprise? My enterprise is to think about the vast ways in which maybe people voluntarily enforce codes of ethics and try to sort out when it happens and when it doesn't. And I've admitted as strongly as I can that there's no way I can do this perfectly. And the anecdotes are only anecdotes. And the models are only models. But what I'm going to do is present a few toys that honor people that I respect quite a bit, that give you a little bit of insight, possibly into the regularities I can do. So the first two people I'll honor are David Krebs and Sam Bowles. Sam Bowles forever has been arguing about endogenous preferences. That is to say, saying that the way that people value things really depends on the institution they're embedded in. And David Krebs, in somewhat recent Arrow lectures and in the third volume of his microeconomic opus, I think embraces the same idea in terms of organizations. And I'm going to sort of implement this in a very, very simple way. Just imagine that there's going to be a binary choice. So there's this event. The ball ricochets off, and Derek Jeter has to decide whether he shakes his hand or admits to the umpire that in fact the ball did not hit him. And there's going to be a choice that gives you a value V of being virtuous. So this is extended preferences. And then there's going to be a value B. Is it true in Portuguese that these are basically the same sound, like in Spanish? In any case, I apologize for that. A value B, which is a benefit for being bad. So Derek Jeter could preserve the integrity of the game, or he could get first base. And there's going to be something that measures the effectiveness of the referee. That is basically how often you get away with it. And then I'm going to allow people to be heterogeneous so that lambda will be a weight attached to V. So basically there's a race between lambda V and 1 minus PB. What you get if you're a good guy, or what you get if you're not. The Bowles-Krebs wrinkle is that people's value for being virtuous is determined in part by how big the referee is. So that by having stronger third-party enforcement, these people intrinsically lower their preference for being virtuous. Essentially, they say, well, I don't have to do it, the referee will do it for me. Okay, so I then get a very simple choice problem summarized by the last two lines. For being good, I get something that depends on my own characteristic by some function of how big the enforcement is and by a value. And by being bad, I get something else. So the easiest way to think about F in this situation is the following. The tiniest bit of enforcement degrades the experience. So there's a categorical change in your preference once you know a third party is watching. Think about that as an extreme case. It's written categorically as number one, and then it's a very interesting, no, not very interesting, very easy exercise to see what happens, how people behave. The answer, roughly speaking, is, you know, high lambda people are good and low lambda people aren't. And the distinction between what is high and what is low is the right-hand side of this inequality. What's interesting in this situation, perhaps, is that the little bit of surveillance can poison intrinsic motivation. And one thing that you can say about this exercise is that if you imagine somebody optimizing over P, they would never pick a small positive P, because that will kill a lot of moral behavior without getting a lot of good behavior through the enforcement. So in one sense, this is a simple model of both crowding out and, if you will, a discontinuous notion of what enforcement will be. It's also pretty clear what the effect of changing B and V are. The ratio is all that matters. Essentially, if you, for me, what's interesting is if you make the benefits higher, then you're going to get more cheating. That's obvious informally. Am I to stop? I'm not sure if this is my time or I have more time. Is this no? So the comparative statics is obvious. The interpretation makes a conclusion fall very close to the tree, but it's still a conclusion. In my notion of the difference between an individual sport and a team sport is that when you're playing a team sport, you're doing something that's going to influence the payoffs of your teammates. You have extended preferences for them, but those extended preferences don't place weight on their own moral values. So if you increase B, basically it's like saying you have more teammates. Okay. I think I say most of this. There's one thing at the bottom that'll come up. In this example, there's any kind of multiplicity of equilibria, if you imagine optimizing over P, is an accident. And at some point, I want you to think of multiplicity of equilibria as an interesting phenomena, because honor codes can be viewed as selection devices. And we'll see that in Model 3, Model 2. So I honor Krebs and Bowles. I honor Benabo Tirole. They have written a series of papers where the reason that people care about something other than money is something about reputation. So I'm going to do something in order for me to look good, or for me to think that I'm good, or something like that. And in this situation, a simple version of that is to imagine that there's something like an intrinsic integrity of the game. What would the integrity of the game be? Are the right outcomes happening? So if somebody breaks the rule, is the person caught? And you could imagine then a situation where when an event happens, I'm trading off, on one hand, my traditional material benefit B, on the other hand, how I'm contributing to how the game is viewed. So is the game fair? And I think I will not say that much here. I've written this page, so I'll tell you what's on it. I is this notion of how well the game performed. B, as before, is sort of the personal benefit. P, as before, is the strength of the refereeing. Mu is the probability that there's an event, that there's this opportunity. This is going to be important because outside observers are going to have to interpret the absence of a decision as either successful cheating or no opportunity to cheat. Again, heterogeneity. I need to make some sort of assumption about what that heterogeneity is to do a computation. So I'll assume it's uniform on an interval. And things are working well if there's no test to the rule, if the referee intervenes and corrects any a violation, or if the player corrects it himself or doesn't do it. And then again, you have a race. You have a race between being good. If you're good, you preserve the integrity of the game, but you don't get the bonus. Or if you're bad, you get the bonus if you're not caught, and you get a fraction of the integrity. And the thing in the brackets is a base rule expression telling you sort of how often people think that there was no call because you were good or bad. Okay, G is the probability of being good. What does that mean? The world is heterogeneous. Different lambdas will be different things. I've given you a distribution of lambdas. So basically, the high lambdas are the guys who are most likely to be good. There'll be a cutoff, and the probability of being above the cutoff tells you what G is. So equilibrium conditions look like 1 and 2. Maybe I'm talking too fast. Maybe there are too many symbols. But essentially, the first one translates the indifferent cutoff to the number of good guys. The second one tells you that lambda star really is the indifferent cutoff. So the first model, the analysis was really easy. The second model is profound in the sense that if you look carefully, 1 minus G is a lambda. So I have to solve a quadratic equation to figure out the equilibrium. You can do that. Me, not so much. So I'm not going to solve it, but I'm going to tell you what happens. From the bottom up, team impact means that the comparative statics on B works as I've said. If you increase B, which I interpret as adding teammates, you get more likely to be bad behavior. Number 3, I said that I had to solve a quadratic equation. When you solve a quadratic equation, you hope to have 2 solutions. It turns out that when you solve this quadratic equation, there's only one economically meaningful solution. And that isn't so crazy because there are no complementarities in this environment that might lead to you intuitively thinking that are multiplicities. Again, multiple equilibria are interesting to me because they're a hanger for the possibility of honor codes or conventions to discipline behavior. Finally, crowding out just means that if you make the referee stronger, you're going to cause more people to rely on referees. One algebraic property is that the crowding out is not, overly strong. If you make the referee stronger, the overall integrity will go up. Okay, model 3. So I bowed to Roland and Jean, I bowed to Sam and David, I bow to Rachel and George now. So their model is a model of identity. All of my betters have more complicated models, I just pick out stylized nuances. I'm going to make model 3 look just like model 2, except that instead of integrity, I'm going to have the player benefit by something that has complementarities. So lambda you're familiar with, that's a heterogeneous parameter. G you're familiar with, that's how many good guys there are. V you're familiar with, that's the value you get from being good in some sense. And what I've changed now is that the value you get depends on how much company you have, how many other people are being good with you. Okay, this is a complementarity. Now, if you write down or try to do the same analysis I've done before, you want to figure out what G is. In order to figure out what G is, you want to figure out who the marginal player is. So lambda star is the person who's just indifferent between being a good guy and being a bad guy. You've seen the extent of my mathematical ability. I can solve quadratic equations. So this is another quadratic equation for lambda. This time I made it more transparent because I substituted in for G. This quadratic equation is different. This is a quadratic equation that will typically have two solutions. A low lambda, which is lots of good guy equilibrium, and a high lambda, which is fewer good guy equilibrium. And this is a thing that in some sense I've been hinting at in the past. This is an environment where there's a role for an honor code. That is to say, if somehow or other in the beginning of time, Cricket wrote rules of behavior, then that could really enforce or at least direct agents to play differently than they would in baseball, where they didn't write that honor code. So again, I repeat, this is a quadratic. I know how to solve quadratics. With right parameter values, it will have two solutions. So there's a role for coordinating devices. And then there's something a little bit interesting here, and that is that the low and the high equilibria have different qualitative comparative statics properties. And I think that I will tease you with that. That is to say, I promise that's looking just at one first order condition, and you are clever enough to tell stories. So I'm nearing the end. No, right? So I think that the first line is and the second line are true but not really meaningful. So the world is heterogeneous. We can find examples in all sports of people behaving in different ways and in all environments. It seems to be a case, somebody can offer a counterexample, that we're not good enough to do it all without supervision. So when Roger Federer was 8 years old, presumably he was playing a lot of tennis, and he didn't have experienced French line judges controlling things, and the games had to flow from some sort of cooperative spirit. And that cooperative spirit appeared in the high school basketball example. But when the stakes are really high, you get people who are watching. Okay, I think that the fraction of good sports varies from sport to sport. I've tried to indicate that. I certainly haven't proved it. It could be that there's some higher level selection so that, you know, Derek Jeter decided not to become a professional golfer because he liked to cheat. But I think that probably it makes more sense to focus on the structure of the game. And I want to attribute the variation to a few things. These things, I think, are all fairly straightforward, but I'm not that clever, and I've learned something from trying to lay it out for myself. So one thing is, do you enforce yourself, or do the referees do it? Another thing is it even possible to self-police? That is to say, when an infraction occurs, are you able to basically announce an infraction with no cause? A third is whether there is a code of ethics. And the fourth is the extent to which it's a team sport. So I don't have anything more to say. So thank you for listening to me, and I'm So, I can hear you, but perhaps it'd be better if everyone.
So your part about integrity, your model of integrity makes me think of research integrity. And I think now what we see is for like people at Harvard, if there's questions of research integrity, the B is high. The B is high, but also the cost is high too. Whereas if you're a person in India who's copying the research of somebody in China on small villages, okay, and what they do, you know, we put a note in economics bulletin about this, saying that this paper was questionable, but nobody cares. Nobody cares, right? Never makes the news. So I think there must be a middle ground, right, where the B becomes sort of relatively small so that it can be dominated by integrity. Mm-hmm. I don't know. Have you thought about distributions like this?
So I'm going to do a standard trick and answer a slightly different question.
Oh, very good.
That'll
probably be a good question.
I apologize. So one exercise you could imagine doing is thinking about the incentives people face in a life cycle or inequality. So Derek Jeter is a star baseball player. What are the differences between his incentives and somebody who will be in the major leagues for only 1 week? What is the difference in the motivation between someone who is at the end of her career or at the beginning? And these things, I think, are somewhat related to this says I'm supposed to stop, to India versus Cambridge. And how could I say it? I have some obvious things I can say that in some sense you know already. I just label these people with B's and B's, and I have some non-obvious things to say that involve what happens if you take any of these games and repeat them, so that there is a role for preserving or lowering your reputation over time. So again, I apologize for not really answering your question, but I packaged it into let's think about the heterogeneity as entering not just in the lambda, but in more of the parameters.
In football, soccer, in the recent World Cup, you saw, I mean, a lot of theatralics by papers who thought they had been fouled. There is a rule in football that you get penalized for simulation or diving. Have you looked at this particular, that the explicit way of trying to exaggerate what happened to you can be possibly punished?
So my answer to that is two parts. First is that I don't know, so I don't have even anecdotes on that. The second is that at the level of my analysis, it's in there. That is to say, the formal story really depends on kind of abstract interpretations of the V and B. And so I don't have to distinguish doing something that's bad and against the rules or doing something that's sort of considered bad. It would be captured by whether the net benefits. So in your case, instead of having 1 minus B, I'd have P minus punishment plus 1 minus b. So the short answer is, in terms of facts on the ground, I know nothing. In terms of what my silly models can do, I think I can incorporate.
Dr. Sobel, thank you for your lecture. I have a question on about what do you think in your models and your research, the impact is of the probability of getting caught being absolutely certain after the fact. The example that I'd like to give is in international soccer on the World Cup that we were in. I took the probability of getting caught that you said as within the game while the game was happening. However, in international soccer, since we have the cameras, something like a handball will inevitably come to fruition. Everyone eventually will know that you cheated on. And how does this impact the model?
There, I think, are very striking examples in golf. So in golf, there are more situations than the referees can observe, but increasingly there are cameras. And so the cameras can post, on ESPN, and then the million viewers will say, so-and-so moved the ball. And there clearly have been examples of enforcement after the fact. So I don't know, in the case of football, whether somebody has lost a goal because after the game an infraction is found. If that's the case, I would interpret this as just better enforcement. If it's the case that what happens is that we learn more about the integrity, but we don't really learn more about enforcement, I think that I would have to have a different P on the left and right hand side of my equations. That is to say, on one hand, there's the probability of getting the benefit. On the other hand, there's the integrity effect, and you divided those things. So again, my first answer is there's a sense in which you can think of this as just better enforcement, but that's limited to whether in fact you can enforce after the fact. If not, then you create an asymmetry, but I don't think that it fundamentally changes the way that I do the simple analysis. I come down. But I come down with water.
So, once a more story of reason, reputation. I'm going to really cause that. I'm going to be nice. And in my meditation, so next time when really close, I can get better. I can be, because people say, well, look, he's a nice guy. He's not going to cheat. He's going to cheat more. And that's, you integrate when you said repeat again. But for me, that's a fact. Exactly. I see. No, I don't know. I think the paper melons one of those game systems. I want to be nice, but something guy. But then there's pretty overwhelming when it's I cannot say that that's wrong. Okay, that's good. I did my occupation. So I cannot say, in terms of
No, I understand. No. Okay, thank you. It's surgically in this room today. There's a lot of different styles. So find one. So I would then approach role. So there are obviously many different ways in which you could train their model, but I think that it's not hard to write a version of their that will have the same flavor as whatever. So I never thought because they were similar in spirit, but had slightly different things. And you could do 300 of them, but I couldn't think of 297 more people. But I think that you're right, that self-stimulating is in the spirit of the second part, and that could make a story like I think that the quotation I put from the golfer, which was repeated by the football player, is exactly. I think that Sergio's comment notwithstanding, there really are people who are motivated. The trouble is that I'm not sure who they are. So I think you have your fine. Oh, you already have it.
I have all this, but I mean, here it says apparently
really
now the semi-plenary lectures.
All I want to do is feel like I understand the margin.
Is it not 14:55? It's already 10 minutes later.
Really? Wait, something's wrong. Just a minute. I'm sorry.
Well, he was good sports. This was his lecture, and then right away it's me.
Guessing better what will happen. I'll never get.
And do you happen to know how big it is? Maybe it's just changed.
Identified a saline.
That's it.
14:55.
Yeah, that was 10 minutes ago. So it's immediately
Oh
after
my. I don't know how that happened. Okay.
No, but what else should it be?
What was that?
Is it not true?
Yeah, no, it is. It is. So you have 1 hour and 10. And I mean, yeah.
Or is it meant to start later? I mean, that could.
Lowering the cost.
Okay, there is no organized transition here, but I think this is my final lecture for the mini course. So thank you for everyone who's still here. sorry. So I have a few, some pieces that relate to computation of equilibria. I will here talk maybe 15 minutes about finding all equilibria of a two-player game. And then I will say something about correlated equilibria, which might be interesting because we had a few talks, for example, by Roger Myerson, where you might have heard of a Markov chain, and it will explain a little bit of the role of this Markov chain in an existence proof. So we start with wrapping up some pieces about the problem of finding not just one equilibrium, possibly depending on a starting point, like in our path following algorithms, like Lemke-Hausen or Lemke, but all of them. This will be a harder task because there might be many, many candidates, and it's even hard to decide whether, for instance, an equilibrium is unique. So we cannot expect this to work for arbitrary large games. But there is an algorithm, and there is a standard algorithm to which I contributed, has been around for a while. There's also a web page. You can upload your game, and it will create a list of all and description of absolutely every equilibrium in the two-player game, even if it's degenerate. So, what are all the equilibria? In a general game, any Nash equilibrium is a convex combination of extreme equilibria. These are, in fact, these vertices of our polytopes. And we can also describe which of these extreme equilibria can be combined to find any other ones. There is a algorithm called lexicographic reverse search, LRS. And then it gives us components of equilibria. One set are so-called convex components, which are maximal Nash subsets, which are equilibria that are mutually exchangeable, like in a zero-sum game. And then they might also create larger sets, which are topologically connected. All this is done by this algorithm. So, little example, a 2x2 game, we have two pure equilibria. We identify them with labels that corresponds to the row players strategies 1 and 2 and column player strategies 3 and 4. We can compute, for example, also the mixed equilibrium with our difference trick. And the way to do is to write down the expected payoffs as functions of the probability of the other player. And then we get the diagrams that you have seen many times here before. Here is a function of player 1, player 2 mixing called Q, and then the best responses of player 1. And the equilibria are the completely labeled points. For example, this mixed equilibrium here, 1, 2, 3, 4. Or another one is here when you have 3, 2, and 1, 4. This is one of the pure equilibria. Again, a label of the own player is an unplayed pure strategy. So what we want to do is we want to find all these completely labeled pairs. We introduce our polytopes. These are the polyhedra with the payoffs, the corresponding polytopes, where I divide by the payoff to get a normalized payoff of 1, which reduces the dimension by 1. Actually, it doesn't reduce the dimension because I also gain a dimension because I don't have an equality here. But that simplifies the problem, the equality that the components sum up to 1. And this was the projective transformation that I mentioned several times. So that transforms the unbounded set to a bounded polytope. Now the question is, and this is one of the main contributions of what I'm saying now, how do I find all the vertices? And this is the algorithm. And it's a very, very simple idea and very cute. And you know that when you have a polyhedron, it defines a set of it's defined by a set of inequalities, and I can run an objective function maximizer via the simplex algorithm, which traverses the edges of the polyhedron until it finds an optimal one. And what we're doing is we're doing this, excuse me, in reverse. Sorry, I need. We're doing this in reverse. So we find a vertex. For example, we know a vertex like the 0 vertex of our polytope. And we can easily find an objective function that is maximized at that vertex. For example, I just take the sum of the normal vectors. I mean, they point always up. If I take the normal vector for this, this, and this, it points upwards, and I know this is the optimum. So I reverse that step. So that means a pivoting step means I follow an edge. For instance, I go backwards. So let's put it this way. Any vertex in the polytope, which corresponds to a basic feasible solution of this linear optimization problem, will have either it's optimal or it will lead to a next vertex which improves the objective function. And this creates, if you wish, a tree of all these flows of edges that terminates at the optimum. And I generate this tree in reverse by pivoting, and then I find the next one. And there is a trick. You have to be careful because you can find all the outgoing edges like this one, and this one, but this is not necessarily part of the tree. So what you do is, in fact, the following. You follow this edge, and then you try to check whether the optimization rule, which you know, which maximizes this objective function, would actually lead you back there. If it leads you to another vertex like here, this is not part of the tree. So what you do is you explore all these edges, but you then only go forwards by those that are actually parts of the tree. So you pivot backwards, forwards, and then you generate the tree that way. Depth first, if you like. It reminds me, I was once in Paris in an institute of, it's called the Laboratoire d'Économétrie, which was located, no longer is there, in a big ministry of whatever it was, a big French ministry. I mean, some people might remember this ministry. And it was very easy to find the laboratory. There was always an arrow this way to the lab. So I could follow this arrow and find my lab. But on the way out, there was no arrow to the exit. So what I had to do is I had to explore all the different corridors. And the one that had the arrow to the lab, that was the one that then would lead me out of the building. So it was a more complicated search. It was not complicated super, because I mean there were only finitely many corridors, obviously finitely many, 3 or so that I could then explore, and only one of them would work, but it was a slightly more complicated. So this was reverse search, if you wish. Okay, and this is what it is. So you have this is what is called LRS. This finds you all vertices of a polytope. So all we need to do is we have to run LRS and then check where the respective vertex of the polytope matches another vertex of the polytope. So we get the 2 vertices list and match for complementarity. But we can do it a slightly more clever way, and that's what I'm also describing. And for this, we have to do a little bit more general, the definition of equilibria, because we look at possibly degenerate games. So the definition is as follows. Well, I have these polytopes P and Q. And whenever I have a vertex, it has certain tight inequalities, the ones that hold with equality. And it will have, at minimum in a vertex M, but it might have more if it's degenerate. So we look at all the tight inequalities that correspond to these labels. We call this, say, the label set K of X, L of Y. And if the union of the two is the full set, meaning the point is completely labeled, then it's an equilibrium. Now, the problem is, in general, that K and L might not be disjoint. They might have common pairs. And then we have actually, in a sense, potentially a whole set of equilibria that correspond, an infinite set that has this as a vertex. So that's what we need to keep track of. The extreme equilibria are the vertices themselves that fulfill this property. And here comes a trick that we use, and it works very well. Normally, when the game is not square, the polytope with the higher dimension has more vertices. Okay, so a 10 by 5, a 10-dimensional polytope. Actually, by the way, they have both the same number of inequalities, namely m plus n, but the higher dimensional one is typically the one that has more vertices. So, however, the number of the smaller vertex number is a bound. So you can only use the one from the slower vertex, from the polytope with fewer vertices anyhow. So what we try to do is we look at the polytope with fewer vertices and then check whether the other one is a complementary vertex of the polytope. So here's the story. We explore, say with this is in a polygon, a very simple path. Here has 3 vertices. I mean, this is the origin that doesn't count, x, 3, 4. And there is a complementary set of pairs. These are the missing labels, which are 4 and 1, but they intersect outside of the polytope. So this is not an equilibrium. And so what we do is we follow only the vertex enumeration on one polytope and look at the complementary ones on the other side. And only when they hit the polytope, we actually start looking at the corresponding equilibria. So that works generically easily. You need a little bit more thought for degenerate games. And we exploit what was known, but which in our paper that I cited at the beginning gives a very compact proof. An equilibrium xy of AB is in the convex hull U cross V of the so-called maximal Nash subsets, where U and V is a whole set of vertices with the property that any two of them are in equilibrium. So these are the maximally exchangeable things. I'll give an example shortly. And we identify them. And then we know that we can take any convex combination of those. And that's what we do. We list them. Well, here is a little bit of technology, but we can look at the faces and Q. So this is what I said. I mean, in fact, these sets U and V are in fact faces of the polytope. That means it is defined by a certain set of inequalities. A face of a polytope is either the entire polytope or a facet defined by a single inequality that is tight, or just some set of inequalities that are tight. When there are enough of them, it's a vertex, but it could also be an edge or a two-dimensional side and so on. So these U cross V sets are in fact faces of the polytopes. So we output these two faces. And they are just vertices if the game is non-degenerate. And let me just, that's not too much important how the details are. There's another algorithm that we can also use in this context. Let me just illustrate what we do with this extreme equilibria. Namely, here's an example. Suppose we have vertices V1, V2, V3, V4 for the second player, U1, U2, U3, U4 for the first player. These are all the vertices that appear in equilibria. We now write a table when any two of them are in equilibrium. And you see, this is such a maximal subset. U1 times V1 cross V2, which is a line segment with endpoints U1, V1 and U1, V2. Okay? Here we have a maximal Nash subset of the form that V2 is fixed, and we have three vertices on the left-hand side, which defines this blue triangle. Or we can have 2 times 2, which is a rectangle. And you see that these sets overlap. And they overlap if and only if their vertices sets overlap. And by the way, here's an isolated one. It's a single point here, just U4 and U4 and V4. So we output not only these convex sets, but also what are the convex components that they then define as unions, which is of interest for some study of games. You might know degenerate games where you have a whole cycle of equilibrium sets and so on. They all come naturally out of this output. So that is a solved problem. And then you typically, and I have a certain algorithm for enumerating these cliques eventually of the bipartite graph that we have here. Not a problem actually, despite cliques looking like difficult problems, they are not when you try to find the maximal ones. And then you output them like you give the list and you say 1 times 1, 2, 2, 3 times 2, 3, and so on. So this would be the output of the algorithm that gives these. So this is one connected component, which we saw earlier here, and this is the second one. So this program outputs really the full structure of the equilibrium set for a two-player game, which is a finite object, a finite list of extreme equilibria. This is something you cannot expect in a game with more than 2 players where you need curves or whatever that need parametric descriptions. You cannot just take them as product sets and their unions. 2-player games are very nice in this respect, as usual. Okay, so that's what I wanted to say about the equilibrium enumeration, as this is normally called. Mind you, this doesn't give you any selection criteria. We do also have an extra program. It's not yet out, but we have it. That would also compute the index of the respective component, if you're interested in it, because components can have bigger indices, which are obtained by perturbing it and counting the indices of the perturbed game nearby. Okay, so this was about equilibrium enumeration for completeness. And let me now continue with correlated equilibria, which is mostly known. And if we have time, we also go to extensive form correlated equilibria, which is a bit more related to my own stuff. But here is something that is known, and which I again think every game theorist should know. It is the existence of a correlated equilibrium without resorting to the fact that the Nash equilibrium exists. It is actually not even via the LP duality so much as via a very nice construction. And let me explain what correlated equilibria are. It's a mini course you might know, but maybe not everybody knows. So let me explain. They are defined for n players, but we will illustrate them for 2 players. So here is a chicken game where you play top, bottom, left, right. You have 2 pure equilibria. This is a symmetric game. You see it by reflecting along the diagonal, if you put the payoffs in the right corners. And you see that 5, 1 is an equilibrium. Why? Because 5 is is better than 2, and 1 is better than 0. So we have a pure equilibrium here. And I describe it now by a joint distribution on strategy pairs. So this is the joint distribution that picks just this left corner. We have a second, by symmetry, a second equilibrium, top right, which is like this one, which, by the way, here you get the payoffs, 5, 1 and 5, 1, 5. Or the numbers are chosen so that the probabilities are simple, very simple to compute. There is a mixed equilibrium where everybody mixes with uniform probability. So every box has a probability 1/4. The sum of all payoffs is 10 divided by 4 is 2.5. So actually the mixed equilibrium has lower payoff, than 5, for example. And now we extend this notion. These are independent distributions on the square on the 4 strategies. Now correlated equilibria extend this to allowing for joint distributions. And the idea is that this joint distribution is known to the 2 players and then drawn as a possible strategy pair whose components are then individually told to the players privately. So if you have, for instance, a distribution would be, this is clearly not uncorrelated, it's correlated. So you pick one of the 2 Nash equilibria. But we can do more than just Nash equilibrium. But let's just do that. We get here, we pick either one. And if, say, bottom left is picked, then player 1 is told that we have bottom, and player 2 that we play left. And then you also know that the other player has been told this, so it's clearly an equilibrium to stay with this recommendation. And you see that it gets a higher payoff, namely 3-3, than what we had before. This is, however, not the only equilibrium, Nash correlated equilibrium. Sorry. There is one which gives even higher payoff, which uses this top left square, which has payoff 4-4. If you play 1/3, 1/3, 1/3. Now, what does this mean? So if I, for instance, pick the bottom left thing out of this distribution, player 1 knows for sure that the other player plays left, because that's the only way he could have been told bottom. But player 2 only knows conditionally that the other player has with equal probability been told either top or bottom. But that still doesn't give an improvement for player 2 to deviate, because she is still indifferent. She gets expected payoff 5 when she plays left, which would be 5/2, 2.5, which is the same when she would play right. So there is no incentive to deviate. And by symmetry, so all these outcomes are possible ways. For instance, top left, neither player knows what the other player has been told, but neither has an incentive to deviate. And when you now add up the payoffs, you get here 10/3, which is 3 1/3. This happens to be actually the socially optimal correlated equilibrium. However, there can be even worse ones. For example, for the same reason, 1/3, 1/3, 1/3, where 0, which is very bad, has maximum probability, in fact, and then the players only get 2, which is even worse than anything in sum that they had before. So correlated equilibria can be beneficial or detrimental for you. In general, the set of correlated equilibria exceeds in terms of its payoff what you can get by Nash. It's not just a convex combination of Nash equilibria. And now what is the general description? The general description says, well, we have here variables, which are the probabilities for the joint distributions. Sorry, for the profiles. Let's call them A, B, C, and D. They sum up to 1 because they're probabilities. They are non-negative. And now come what is known as the incentive constraints. They say, If you have been told a particular row as a row player or column as a column player from this distribution, you will have a conditional distribution on what the other player has been told. In this case, say, if the top row has been chosen, then you know the probabilities for the columns are A and B divided by A plus B in both cases. Now, you can forget about the factor 1 over A plus B, because the incentives are the same. So you say the expected pair of what you get is 4 times A plus 1 times B, has to be at least as large with the same probabilities as 5 times A plus 0 times B, because that would happen when you get told to play bottom, but may consider deviating to play top, so deviating to play bottom. And you can actually simplify this. You see this is the same as saying B is greater than or equal to A, the first inequality. Similarly, when you told the bottom row, your conditional probabilities for up to normalization for what the other player has been told are C and D. So 5 times C plus 0 times D, which is the expected pair of conditionally on staying with bottom, should be at least as 4C plus 1D. The same probabilities against C and D, but you now look at the payoffs when you switch. And this can be simplified to C greater than or equal to D. Now, by symmetry, this is a symmetric game, not in general it isn't, but you get similar inequalities for the column player. So you have here 4 inequalities in addition to the non-negativities that define a polytope, which is the polytope of correlated equilibria. And you can do this exercise for any number of players, and it will be a linear system, unlike in Nash equilibrium. It's a convex set as well. So it is computationally a relatively easy object, although you have a lot of combinations. So these are called the incentive constraints for this particular example. Let me see. For this particular example, I also have a, let me see whether that works. Permit here. These inequalities, let's see how long it takes. Yeah, I have, I drew it, and in fact, you can make it animated. Let's see. Let's rotate it. Yeah, I have something for you, Roger. Look, this is an animation of the correlated equilibrium set. The green set is in the simplex of the 4 corners of the strategy set. Maybe we can slow it down a little bit. The set of correlated equilibria. And what I've drawn here, let's stop the rotation. Stop. You can also manipulate it. And what I've drawn here, so top left, bottom, so anyhow, this is the simplex of the 4 corners. This is the green set is the set of correlated equilibrium set. And if I intersect it with the set of independent distributions, the product distributions, you get this nonlinear object. Also, it's in each component, it's linear. The intersection of this set with the correlated equilibria is exactly the set of Nash equilibria, which are here the top right, bottom left, and mixed Nash equilibrium here. So you see that here. Okay, something to play with. Let me check it here, and let me go back. Okay, so to repeat, the set of correlated equilibria is a polytope defined by linear incentive constraints that compare any 2 strategies of a player. If you will think of it in terms of variables, these are the probabilities for strategy profiles. Can done it for any number of players. And you can, for instance, easily find the correlated equilibrium with maximum payoff sum. There's also a nice story, now with learning in games, with certain so-called internal regret matching, you actually approximate also the set of correlated equilibria. And this comes out of an existence proof that I want to talk about next. Well, that's a very brief way of doing it, but now I show you this existence proof. Not mine, it's actually by Sergio Hart, who is here, and Schmeidler. And parallel, it was at the same time, 89 or 1990, discovered by Now and McCardle, almost the same proof. And Roger has written a paper on it, dual reduction in elementary games, that comes out of this proof. So here's, the general setup. So we say Si is the set of pure strategies of player I, S minus I is the set of profiles of all but player I, and I write down here the payoff to player I with a superscript, U superscript I, when she plays strategy A in SI, where S minus I is fixed. Okay, so that's what she does. And the incentive constraints now say the following. For any pair of my own strategies, A and B, if I look at this, suppose this is the row player, or we put them in the rows. SI is now the set of rows. You are recommended to play row A from this joint distribution. And now you have SZ, which is this distribution. Yeah, I mean, Z is the distribution S on the strategy profiles. Now, Z of A comma S minus I is the row of all possible probabilities of what the other players have been told in their combinations, given that you have been told A. Okay? Now, you are meant to get payoff UI times A of S minus I from that in expectation. If you switch with this for the same distribution to B, you have to subtract that and it has to be greater than or equal to 0. I mean, obviously I could write this as inequality between two sums, but this way I have concentrated it in order to have the probabilities only once appearing in this row. So you multiply the probabilities in that row with the corresponding payoffs, minus the payoffs that you would get when you switch. And you don't want to switch. If you do, if this was negative, you would have an incentive to switch, but you don't want to. If these incentive constraints are fulfilled, it is a correlated equilibrium. And a Nash equilibrium is a special case because then this ZS A, S minus I don't depend on A because it's independent, okay? So that's why Nash is a special case. Okay, and now comes the existence proof. It looks messy, but it is a way of, it's just algebra, but I try to guide you through it. We have a little bit of time, and then you will probably hopefully not be too scared when you see it alive. So we do it. It can be done with VLP duality, but it can also be done via an auxiliary game, which is zero-sum game. It's a big game. It has two players. It has a row player. I also like to call it the correlator. And any possible combination of strategies, any profile of pure strategies is a strategy of this row player. And the interesting part is, so this is a lot of strategies, obviously, who mixes with a distribution which will become a correlated equilibrium, if it works, if it is a optimal strategy in this game. And the column player has something interesting. That player chooses I would like to call that player the deviator. This is the kind of person who tries to induce you to deviate from what you have been told. And this person does the following. She chooses a player I and a pair of strategies for this player. In general, she will use the mixed strategy, this deviator, which I call Y superscript I and then AB, but for any player I and any pair AB, that's a strategy, certain column in this game. And now the payoff to the row player is the following. If the player chosen by the deviator and the strategy for that player chosen by the deviator matches the row. So in other words, this strategy A appears in the strategy that the row player has chosen, then I subtract from it what you would get when you switch to B. So that's the payoff to this row player, which is now this meta player in this game. Otherwise, nothing happens. So now here's the story. If the game has value 0, then I would be able to, as row player, to guarantee a non-zero payoff, a non-negative payoff in each column for any possible deviation. And that would mean that all the incentive constraints are fulfilled. So that would mean that I have a correlated equilibrium. Okay? So if the value of the game is 0, there is a max-min strategy that is, in fact, a correlated equilibrium. Now, on the other hand, so let's call this big game with payoff matrix capital U. So the expected payoffs are Z times U times Y. Z is the purported correlated equilibrium, if it works, and Y is the deviating plan. Now, what you will observe is that you can always trivially insert payoff 0 as the column player, because you could decide never to deviate. Yeah, you choose only, say you choose a single player and an A and an A. Then this difference is 0 and nothing happens. Yeah, you are guaranteed to pay at most 0. So the value of this game could not possibly be anything, if players play optimally, anything other than 0 or negative number. Okay? So if the game has value 0, then a correlated equilibrium exists. But the game value of the game could be negative, and then we would be in trouble. And now what we have to show is that the value of the game is not negative. And this is the trick. That's the aim. So let's repeat. I mean, if we have a correlated strategy Z and deviating strategy Y, then we get this payoff, which is just the expected payoff here, as we do it for Z, and then multiply it with YIAB. And now the trick to show that this value is indeed 0 is indirect. It says, if there was a deviating plan that would create a negative value for all rows, if the value was negative, I prove you that this cannot be the case. How? I choose a specific counter answer, which I call, well, essentially you have to show that the value is actually, whatever Y is chosen is actually non-negative, but it suffices to show it is 0, because then it cannot be negative in all rows, because the convex combination of rows that is negative would stay negative. The X that I choose would be, which proves that it's equal to 0, refutes that. So this is an indirect way of showing that the value is actually 0. And the special story about this proof is that the X is actually chosen. It's not a correlated equilibrium or anything. It's not even a Nash equilibrium. What it is, it's a special uncorrelated strategy, namely a distribution on the strategies of a single player, which I call X superscript I of SI. So it's an independent, a product distribution. Each player does something. Now, the main story is what this player actually do has a very nice interpretation, namely, they neutralize this deviation plan. So there is a joint strategy for the column player, and it will turn out that it can be interpreted as a certain Markov chain, which I will explain. But it will be neutralized by finding a stationary distribution for this player that neutralizes the deviation plan in the sense that when you apply it and then you deviate, you get the same distribution, and then therefore it cannot be the case that you deviate profitably, because if it's the same distribution before afterwards, you have not profitably deviated. That's the general idea, and it comes out of the algebra that we now see. So let's look at again now at the expected payoff, where I now substitute X, which is this product distribution. So I sum over all players I about the opponent's partial profiles, about my own pairs of strategies. And now I split out this X of S as a product of the probability for my own strategy A and the X of the S minus I, which is the product of all what the other players are doing. Now here's this difference for the incentive constraint, and here's the YIAB. Okay. Now, by sorting this out, I can already take the X of SI out of this summation because it's the same factor for all these sums. So I only have to look at this box, which is a special sum, namely the sum over the AB of SI, XI of A times UA of ISI times the YIAB. And now I've actually taken it out, and XIA of UIBS minus I, again YIAB. Okay, this is just trivial manipulation. And now all I'm doing is I'm resorting this difference sum according to the payoffs rather than these probabilities. So instead of having XIA here, I want to make sure where does this payoff UIA, SI, UIB, SI appear. And for that reason, I simply change, it's just a formal change. I change the variables in the right sum. So instead of summing over A on the right, I sum over C. All I've done is I've renamed the variables. And now, instead of summing over B, I sum over A. Yeah, so I've just changed notation. But now you see that I have here a sum over A's where UI of ASI appears on the same place. And now I resort this by taking out the UIA of SI, and then I get a certain set of coefficients, which is the XI of A. That comes out once, times the sum of these guys, times the sum of the CSI minus this one. So this is just a consequence of the algebra. And now what we do is, and that's again a very interesting observation, everything we do now doesn't even depend on the payoffs at all. It just looks at these probabilities for deviating and looks at the own controlled, and it's only for a single player. You don't need to look at the other players either. So you try to find now xi of a's, which are probabilities for your own strategies that fulfill this equation, which we now look at in a little bit more detail. So the game is, the aim of the game is to set this bracket here to 0 for suitable xi of a, depending on what yi, a, b are. Now what is this? So this is a square matrix, if you wish, because it has possible rows A, and think of it as a matrix. Y superscript I is a matrix with as many rows and columns, a square matrix, as the number of SI, the number of strategies of player I. Now, this is the first coefficient, this is the second coefficient, and I've summed over the B. So I've looking here at a certain row of this matrix summed up. So we look at this sum of probabilities Y, I, A, B in that row. And what we're doing here is we now sum over a specific column A, xi. So now I sum over a specific column. The column, this is the second coordinate A, and I multiply that column with C. We go over the C's and multiply the entries in that column with xi of C. So what have I done? I have here a certain product. Okay, and now there is a certain, so let's look at this equation again. Here it is. And now it turns out the best way to look at it is you could scale this and think of it as a Markov chain. An even better way of doing this is to look at this equation here. We want to find certain xi that fulfill this equation. In this equation, the diagonal elements where b is equal to a or c is equal to a appear twice and cancel out. So we can ignore the diagonal elements YAA or YAA here, which can also mean that we can do anything to these diagonal elements without changing them. In particular, I can increase them to become a sum so that, these are all probabilities over all strategies of all players, the YABs. So the sum of these things is certainly never more than 1. But now what I improve is I improve on each diagonal element. I inflate that diagonal element so that the row sum is equal to 1. Okay? Then I do get a Markov chain. And this expression says that when I multiply the vector x from the left to this Markov chain, and I look at what comes out at the right, it's the same distribution. By the way, no, sorry, this is what I'm saying. This coefficient then becomes 1. It says xa is equal to to xc times yca. In other words, this is the x times the Markov chain matrix. In other words, it's a stationary distribution of the Markov chain. Okay? You could also do it differently. You could rescale these rows. You would have a problem when the row is 0. The scaling is not so easy. But when you extend it to a 1, that's trivial. Then it's a 1 in there. It's not scaled. You can make easily mistakes with the scaling. Papadimitriou has done it in a paper where it didn't work because he was too quick. If you do it with the inflation, it's a much better approach. So anyhow, the interpretation is that x is a stationary distribution that neutralizes the deviation plan according to y that the adversary has given you. And therefore, there is no gain. That's the wonderful thing of the interpretation, okay? By the way, I've not seen this before with the diagonal elements. I put it in my book. It's chapter 12 of my book, which is why I think everybody should learn it that way. So, okay. And therefore, the value of the game is 0 because I can neutralize any deviation plan. Hence, it's not a constructive proof, but it's a proof a correlated equilibrium exists. By the way, the xi's look a little bit like distributions, independent distributions like Nash equilibria. They are not. Why? Because the value of the game is 0. So, for example, the adversary could never deviate. Everything is the identity matrix. If you have an identity matrix as a Markov chain, everything is stationary. So you get no information about this behavior unless you look at special cases that might make it more interesting. Okay, you can also generate an algorithm out of this. Yes?
Those are the feasible strategies for players.
Yes.
That's it.
Okay.
That was my talk.
Okay. So,
nobody understood then.
Okay, exactly. That's why I'm saying it's something you should know once you saw Roger. This is okay. Again, it's something I think everybody should know. So, by the way, you can extend this problem to games which have compact descriptions. So one of the problems is sometimes a game is easy to solve, like the correlated equilibrium, but for the wrong reason, namely that the input is too large. So for example, if you have a multiplayer game and you can say an extensive game, I'm talking a bit abstractly, I will come to it. Yeah, I should end at 5 past. So I have 15 minutes. Look at an extensive game. Treat every information set as a single player who can make a choice, meaning a move, independently of what your own strategy. So this is a team of players. You are a player. You have many information sets. You put an agent at each information set. Now the agent has the same powers as you, but they act independently of the other agents. And so this is what is called the agent form of the game. Okay, the agent form of the extensive game. A behavior strategy is like a mixed strategy for this agent form. Now, the problem is that even if you have a small game tree, you can have a very large normal form of that game, agent normal form. And so it's easy to compute a Nash equilibrium, a correlated equilibrium by linear programming, because linear programming is easy to solve, I mean, for a thing, but it's only easy in the size of the of the normal form of the game, which is exponentially large. So is it easier when you only look at the extensive form? And interestingly enough, for the agent form of an extensive game, as a special case of what we have, this works. This is an algorithm that is due to Papadimitriou and Roth garden. And so, for instance, you could have another example. It's an anonymous game. This is a game with many players, the same actions, but the payoff is only depending on how many players play a certain strategy, not which combination. That's a much smaller game specification, but again, you have all this exponential number of who plays what, say n players, 2 strategies, 2 to the n combinations. An anonymous game only needs n plus 1 specifications, namely how many players play the first and how many play the second strategies. So there are many compactly specified games. If they have the following feature, the number of pairs is small, polynomial, the number of actions is small, and it's easy to polynomially evaluate product profiles, you can get actually, as an extension of this proof, and correlated equilibrium in polynomial time. And I spare you the details of how to do it, but it works. So now, so that's interesting. It can be extended to an algorithm for even compactly specified games. Compact means that these descriptions like number of players, number of strategies, number of evaluation of strategies is easy to do. There is an open problem and it's still not solved to this day. And that's why I want to go to my final part. Namely, when you have an extensive game with perfect recall and you don't look at the agent form, but at the standard form, then we don't still know. It's not compactly specified because the number of strategies is exponential. And in a correlated equilibrium, when you write down the big normal form, strategic form of the game, you in principle have a distribution on these strategy profiles where every row could be a different distribution. Yeah, because you have exponentially many things that you could be told. Should that matter for finding an equilibrium? And intuitively it shouldn't, but we don't know how. And you know that for Nash equilibrium, we have the sequence form that I talked about yesterday. We don't have such a thing for the correlated equilibrium. But we have a concept that we have developed in that context. I was asked this question 30 years ago by Nimrod Megiddo about how we can compute correlated equilibria. And then I talked actually to Roger, to you as well, and then to Françoise. Can we maybe find another concept that would get it close in spirit to this, to say behavior strategies? And this is my final talk of the whole mini course, which is called Extensive Form Correlated Equilibria. I give you the main idea. So, what is the main idea? This is the paper. It has been cited 170 times by now. Well, it's already 16 years old, but 18 years old. Now, this is a bit, so what is the story? What's the main idea? This is all, so here's the idea. Instead of recommending strategies to the players, I draw a pair or a strategy and use a joint distribution on the set of strategy profiles. A strategy is a instruction of what to do at every information set. But I deposit, imagine it to be deposited for every information set, the corresponding recommendation, and you only open your recommendation when you reach that information set. In other words, you only get a local recommendation what to do, but you know you will also be told something later on. So unlike the agent normal form, where you only open it once, you're still in control of your own future, which you should be when you play an extensive game, right? It's not an agent, me tomorrow is the same as me today. So I should take into account what I can do tomorrow, but I don't know what it will be. So that's the main idea. And here's an example from Roger. It makes also sense in a certain communication settings. Here's an example where we have a battle of the sexes now with all zeros when you don't coordinate, which is 5115. And you know that one of the correlated equilibria of this game is where you play either top left or bottom right with probability a half each, which is an expected payoff of 3 for both players. It's a good outcome. But when you precede it by an outside option where you get 2-2, you see that this outside option dominates the case where you would go to the bottom right corner for player 1, because if that player would know that they will only get 1 in the corner, they'd rather take the outside option. So you lose the payoff 3-3 if you give them every advice at once. But if you delay, if you choose, say, the 3, say your equilibrium is a half here, a half here, and you pick that thing, so you would be told you go in, your expected payoff is 3, you would take it because the expected payoff is 3, and now you open it and say bottom, oh, what a shame. But it was the right choice because in expectation it was 3. So you gain this bigger payoff by not applying it to the strategic form of the game, but for this delayed system, or it's an example of my extensive form correlated equilibrium, the one with Francois. Okay, and you can also prove that it's done also with, you can even use reduced strategies only. And the incentive constraints, you can imagine that they're not easy, but they use actually the sequence form for in general, for the constraints in the future. So you can have, you don't need to look at all the possible deviation strategies. You can compactly encode them as you do for Nash equilibria. There's also something interesting. By the way, this is not the agent form, because here, out B is an equilibrium in the agent form because you get 0. But if you were in control of your future self, out B would not be an equilibrium because you know when you stay in, you can then change to top and you get better. So clearly you are in less, you have more power when you look at our concept rather than the agent form. Okay, now the interesting thing is, and this is a bit technical detail, but it turns out with chance moves, if you don't have chance move or if you have public signals, you can even write down a set of inequalities. So for 2 players, only public signals and no third player, you can write down a sequence form for the extensive form correlated equilibrium, which is a small polytope, which is like just doing what I did in the sequence form in both rows and columns. I call them correlation plans. And it's a small description of the polytope that would describe this set of extensive form correlated equilibria. For 2 players, public chance moves, this works. It does not work when you have a chance move. You only get valid inequalities, but they might be more complicated for the actual strategies. And then you can actually prove in this part of the paper that, that this is even difficult to compute. It cannot have a small description because it would otherwise prove that NP equals P, which is a big open problem. You would solve an NP hard problem with these small number of inequalities. That's all in the paper. And you can, there is, the notation becomes complicated, but you can even, I didn't say this, but you can actually extend the existence proof of Hart and Mascolel and to an algorithm like Papadimitriou and Roughgarden, even to the extensive form correlated equilibrium to find one correlated equilibrium in polynomial time for a general game. This is joint work with a PhD student of mine from China from 2011. So in the interest of time, I should stop, but I hope I have shown you quite a few things that you can do with the inequalities, linear inequalities. I think an interesting research topic that arises out of this is actually coming from the learning community, from the people who do learning in games, because they find extensive form correlated equilibria by learning by regret matching in extensive games. So that's one of the reasons we have so many citations, because people like this concept. By the way, I mean, I didn't say that, but in the existence proof, remember we had this deviator. This was the column player, the artificial column player. Now the question by, and that's what Sergio told me, Sergio Hart, what if we run fictitious play in this auxiliary game? It's a zero-sum game. Fictitious play in zero-sum game converges. What should it converge to? To a minimax solution, which is a correlated equilibrium. So the concept of regret-based learning, where you compare what you could have done when you chose switch from A to B, which is now known as internal regret, originated with this existence proof. So that's another reason to learn the existence proof, because it gives you an idea. It was a lot more complicated than that, right? I mean, Mascolel and Hart had, I mean, several econometrica papers coming out of this, but this was the story, the origin, and it originated with that. And so there is a lot coming out of this existence proof for correlated equilibria. Okay. Anyhow, I hope you enjoyed the whole mini course, and thank you very much for your attention. Can you use the mic? Sorry, I mean, you're talking about a paper by Aumann? No, it's off. Is it switched on?
Hello. Okay. I have a question. So I know the paper from the Bob Aumann from the 70s that he works with the correct equilibriums, and he used the model router. And he have this economic interpretations, and so that I have met in 21 in COVID the book Game Theory Basics that you have here introduced it, and now I have another approach, and the guides which I have used zero-sum games. What is the now improvement of this your last work from 200 to 2021.
2021.
So you have used today the probability that you have.
What I have just talked about is in my book. I have reported on. I mean, the only novelty in my book is the Markov chain not obtained by rescaling, but by inflating the diagonal elements. That's the only novelty, but it's in the book as well. I mean, so that's. I mean, and Aumann, the 74 paper introduced correlated equilibria as a concept. There's another 87 paper, which is said is an expression of Bayesian rationality. I didn't refer to that. I do cite Aumann in my chapter because he told me when Maschler was there in Jerusalem, I was there 30 years ago, he said they talked about mixed strategies and they wondered how people implement them. And they said, well, if you, let's say, shall we do research or shall we play tennis? Well, we do it by looking outside, and if it rains, we do research, and if it's sunny, we play tennis. That's a random event that determines our strategies. And he realized that this is not an uncorrelated event. I mean, if you lose the weather, it might be different from you at home, and in particular in London, it's different when you're 12 kilometers apart, or even 2 kilometers apart, but it's correlated. So the concept of correlated equilibria apparently come out of this conversation between Maschler and Aumann, and then he developed it into this concept. I use this as an anecdote in the first paragraph of my book. It might have been the only thing that Aumann read when he got my book, but anyhow, he put a nice quote on the cover.
We still have time to one more question.
Kostya.
Well, one of the main criticisms of correlated equilibrium always was that the set is too big, right? There are too many potential correlated equilibria, and it's hard to pick one, for example, as compared to normal Nash equilibria.
Yeah.
So could some computational considerations help us to do a refinement of this set, saying, okay, this equilibrium is kind of this distribution is more likely than some other distribution and should be used as a prediction of the game?
Predictions are hard. I mean, but I mean, you could, for instance, look for the socially optimal. If you weigh, I mean, you could take any linear combination of the utilities of the players. You maximize over the correlated equilibrium set, and you take the extreme point. Could be extreme set, but generically it's maybe the extreme point as the most desirable solution of that game. You need to also think of, I mean, how do you implement correlated equilibria? I mean, people always say a traffic light is in a correlated equilibrium. You have a mediator, which is a traffic light, and you have the incentive constraints is that you don't run the red light. Okay, at least when you're a car. I don't do it as a bicyclist, but it's a recommendation that you tend to obey. But then it's already an established mechanism. I mean, when you say, will this appear? Where do the mechanisms come from? I think the fact that we have this regret-based learning is one way of making correlated equilibria more popular, at least than Nash equilibria, for example. It's the same question. So, I mean, but I'm not sure whether they will choose the socially optimal one. I don't know. I mean, but the socially optimal one has a definition if you give equal weight to the probabilities of the players. Of course, that's a choice. So, partial answer. Yeah. Yeah, please, of course.
Correct me if I'm wrong. I think the sense of the question was that a bit of irritation that we have correlated equilibria that are a larger set than Nash equilibria, and therefore there's less determination of what's going to happen. The goal of our analysis is not necessarily to determine what's going to happen. In some sense, correlated equilibria is a set of socially self-enforceable plans of action. And if we want to give a society that has politics and freedom of choice plan for how to behave, it's helpful to give them a larger feasible set, which they can, through democratic political processes, perhaps reach an agreement on how to do. So we're not necessarily trying to predict the future. We're trying to understand what is and isn't feasible. What we're really saying, things that are not correlated equilibria, if that's all that there is in the behavior, then some self-interested party is going to undermine the social coordination. But if it's in the correlated equilibria, it's feasible for people to trust each other that they will do that, and being able to tell society that it has a larger trust set, I think that's progress.
And you also get higher payoffs in general. As we saw, well, in an example, typically we get higher payoffs.
Well, thank you very much, Professor.